Hello all, welcome to the Security Tube Linux Assembly Expert course and certification introduction video. My name is Vivek Ramachandran and I will be your course instructor for the SLAE. Now in this introduction video, I wanted to tell you briefly about what the course is, what we will cover and what to expect from it once you successfully finish it. So SLAE is basically geared at teaching you 32-bit assembly for the Intel Architecture 32 family of processors on the Linux platform. Now make no mistake, this is not simply just an assembly language programming course. Rather, this is geared towards InfoSec and will look into how you can apply your newly learned Linux assembly skills to topics such as shell coding, writing encoders, decoders, cryptors, and other low-level applications which require a decent mastery over assembly language. Now we will be starting absolutely from scratch, which is I would teach you how to write the first Hello World program. Then we would move on to more challenging items such as writing loops or probably going ahead and even writing code for FPUs, MMX and all of that. But keep in mind, I've made this video series, that is this course, very beginner friendly, just like all my other courses. So if you do not have any prior programming experience in assembly or in other languages, you should still be able to pick up this course pretty okay. Okay, let me run you through the course syllabus. Now, I will talk about the very basics of computer architecture, move on to the IA32 and 64 family of processors, from where we will look at compilers, assemblers, linkers, and then the different CPU modes and addressing schemas. Now, this is a very hands-on practical course and we are going to be using a lot of tools such as NASM, LD, Object Dump, NSDisasm, and a bunch of others. Now, after we look at all of these basics of setting up the environment, understanding how the Linux operating system works in conjunction with the CPU, then we will go ahead and look into IA32 assembly language and create simple programs to run on the Linux OS. IA32 language would include understanding of the registers and flags, program structure, data types, how do you move data back and forth between CPU, memory and all of that, reading and writing to and from memory, conditional statement, loops, function, prologues, epilogues, procedures, exceptional handling, and a bunch of other things. Then we would look at things specific to Linux, such as how to use the syscall interface, then after that interrupt 80 and all of that stuff, and then move on to some more advanced stuff, which is using the FPU, MMX, SSE and SSE2 and writing assembly using their instructions. Now, as you can see, the first part of the course is clearly geared towards providing you all the basics you require to understand on how to write assembly language for 32-bit systems. Now, the second part of the course essentially deals with applying all the knowledge you've gained to the domain of information security. This is where we will start from the very basics of shell coding on Linux, look at how do you get running with an execution environment, create actual shell code from scratch for exec, exit, bind and reverse TCP shells, stage shell code, egg hunters, how do you use shell code from third-party sites and understand how they work. So you might have seen a lot of shell code on ExploitDB and a bunch of other websites. How do you understand what's going on in them and use them effectively. Simulating shellcode, how do you locate the different system calls? How do you graph what is happening inside shellcode for better understanding? And then we will move on to encoders, decoders, and cryptors, which is probably one of the most interesting topics out there from a low-level assembly applied to InfoSec perspective. Now, many of you have used Metasploits, XOR, Shikataga-Nai encoders to evade AVs and to do a bunch of fun stuff. But what goes into writing your own encoders, decoders, and cryptors? This is exactly what this part of the course will look at, where you will learn how to write your own encoders and even go far beyond looking at existing encoding schemas to actually creating your own custom encoders, right, which could use random sequencing, other mathematical functions, and things like that. From there on, we will touch upon one of the most interesting topics as far as low-level assembly application to InfoSec is concerned, which is polymorphism and polymorphic engines, right? This is a very hot topic when it comes to viruses, malware, or to create shell code, which is difficult to detect and fingerprint. Once we are done with that, there'll be a bunch of exercises. I will share with you a mock exam, and then you can actually give the certification exam if you so desire. Now, some of the videos, basic theory ones, will be made available on SecurityTube, but most of the videos, exercise solutions, etc., are for registered students at this point. As a registered student, you would get HD downloads for all the course theory videos, all the exercise videos as well, because almost every theory video carries with it multiple exercises, which is where we will practically do a lot of interesting things. Registered students also get PDF slides, all the assembly language code snippet, little scripts which I use here and there to facilitate compilation, disassembly, and all of that will be made available. In the end, you will also get a mock exam and the option to give a registered certification exam after the whole course material you've kind of gone through it and are comfortable. And if you pass the exam, you would get a PDF certificate. Now, for this low-cost course, there is currently no student forum available, just like what we have for the GNU Debugger Expert course. Now, it doesn't end here, because you're obviously thinking 32-bit is just the beginning, and you're absolutely right about that. Now, once we finish the 32-bit course, we will also offer other affordable courses for 64-bit assembly on Linux, then 32 and 64-bit on Windows, and even on ARM assembly. So stay tuned. This is all I had in mind for the SecurityTube Linux Assembly Expert course and certification as introduction video. Click on the link below, which will take you to the registration page where you can register for the course. If you have any other questions, again, you can click on the same link and go and fill up our form, and we'll get back to you as soon as possible. Thank you very much and have a great day ahead, and hope you register and enjoy this course. Thank you. Hello all, welcome to module 1 of the SecurityTube Linux Assembly Expert course and certification. Now in module 1, we will look at assembly language basics on Linux systems, and we will specifically be looking at 32-bit assembly on Intel architecture. Now before we begin into the nitty-gritty details of assembly language, the first question which of course arises is, what is assembly language? Now, if I were to quickly summarize what assembly language is, well, it's a low-level programming language with which we can communicate directly to the microprocessor. Typically, assembly language is very specific to the processor family and has almost a one-to-one correspondence with the machine code the processor understands. Now, what does all of this mean in a layman's language? Very simply, your processor only speaks machine language, which is binary. Unfortunately, we still haven't mastered speaking in binary or machine language. And this is where assembly language basically acts as a bridge. Now, we as humans or as good programmers write what we want the processor to do in assembly language, and then we use an assembler and linker, which are two programs we will encounter later on in this video series, which go ahead and translate your assembly language into machine language which your processor can understand. So this is a very simple illustration. This entire course is on how do you master this assembly language and have the processor do your bidding. Now, if we were to pick up how assembly language is related to more high-level languages like C, then your C source code file would first go through a preprocessor stage, which then passes through the compiler, which would output an assembly language file, which is an input to the assembler, which would give an object file, and then the linker would take your object file, any other shared libraries, etc., which are required, and then output the actual executable, which in the case of Linux would be in the A.out format or the ELF format, and then finally is loaded by a loader for execution, right, whenever you want to run it. Now, one of the most important things is, unlike high-level languages like C and Java, which are very, very portable, assembly language is very specific to the processor family. And sometimes even between different processors, there are instructions which may differ and which are very processor specific. So for example, one of your latest i7 processors may have a couple of assembly language instruction which your older 386 or 486 family may not understand. So what this really means is we need to understand assembly language for a very specific processor, and this is not portable. As an example, Intel assembly is very different from ARM assembly, which is different from MIPS assembly. Now, Intel architecture basically specifies assembly language for two families. One is the IA32, or the 32-bit assembly as it is known, and IA64, which is the 64-bit assembly. In this course, we will look at IA32 assembly and see how we can learn assembly language and run it in programs in the Linux operating system. Now, we will be looking at creating future courses, probably just after this one, where we will look at 64-bit assembly on Linux, and then 32 and 64 on Windows, and even ARM assembly. Now, if you're asking yourself the question, why learn 32-bit assembly when the world is moving towards 64-bit machines? Then the answer basically is, even today, a large number of machines out there are still running IA32 architectures. And without knowing 32-bit assembly, it may be difficult to grasp many of the more complicated concepts of 64-bit assembly. At the very same time, 32-bit shellcoding, encoders, decoders, packers, anything low-level relating to exploit research and reverse engineering is typically very different from what you would encounter in the 64-bit world. And hence it is important to understand IA32 in its own right properly before moving on to IA64 and more complicated architectures. Okay, so without further ado, let's go ahead and do the very first lab exercise. And this is installing Ubuntu 12.04 LTS 32-bit edition in VirtualBox. Right, so The solution videos are available only to students, so please register for the course to get the solution video. This is the first exercise. The second exercise is figuring out details about your CPU on the Ubuntu system, right? So how do you know if your CPU supports 32 or both 32 and 64 bits? If your CPU has capabilities such as FPU, MMX, SSE, SSE2, etc. How do you find out all of these details on your Ubuntu system before we move on to looking at assembly language in more detail? Registered students can download the solution exercises. You would receive it via email and you can have a look at that. So that's all for this video. Thank you very much for watching and see you in the next one. Hello students, welcome to exercise 1.1. The topic was what is assembly language. Now let's go ahead and create the lab setup, which would actually be a 32-bit desktop edition of 12.04 LTS Ubuntu, and we will install it in VirtualBox. So please download the 32-bit desktop edition from Ubuntu's website. This is the desktop edition, keep that in mind, and it has to be the 32-bit one. Second, download VirtualBox from virtualbox.org and install it with the VirtualBox extensions. Now I leave both of these exercises to you, the download as well as installing VirtualBox. From here on, let's go to VirtualBox and create a new machine. Now note, if you're using the Windows version of VirtualBox, the interface may be a little different, but pretty much the flow wise most things would exactly be the same. So I create a new virtual machine. Let me call this SLAE lab machine, and I'm going to select Linux, Ubuntu, RAM, let's give it at least a gig. I'll go with the default options, giving it around 8 gig of space, right? And then I'm going to hit on storage, and I'm going to select my Ubuntu ISO, which I've just downloaded, right? Ubuntu 12.04.1 desktop i386. There we go. And now let me go ahead and start my SLAE lab machine. So right now we are booting from the ISO. And after this we'll get options with which we will install Ubuntu 12.04 on our virtual machine. So we're going to do install Ubuntu. Erase, go with all the default options really. Right, and now the installation has started. I'll pause the video so that I only show you meaningful places during the installation. Of course, really you could just go ahead and set up all of these things while the installation is happening, the keyboard layout. And guys, if you're unfamiliar, there are tons of videos out there on YouTube on Ubuntu installation, which you can have a look at. Name security tube, This is the username I'm picking. You can pick any password you like. Let me just use security tube as the password. Yes, it's a weak one, I know it. But that's the one I'm going to remember, right? Simply because I'm not going to use this VM for anything more than local demos, I'm just going to do login automatically, right? It's more of convenience. Also, there's nothing really inside the VM which requires me to kind of password protect it at this point. And I guess this is where it's drawing a balance between paranoid about security and really only to have security when you need it. Okay, so I think the installation has started. I'm going to pause the video. Let's go to probably just meaningful locations, and then I'll show you, right? Okay, so the installation is complete, and let me just quickly click on restart now to restart it. Pausing the video again so that we can come back after the machine has restarted. Okay, now that we've booted in, let me open up a terminal and ensure that you're connected to the internet. Let me go ahead and increase the font size a little bit. And let's do a quick if config. And if you notice, this is the address it's showing us because we are in NAT mode. Just ensure that you're connected to the internet like we are right now. Now there are a couple of things you would need to do. First is let's push install a bunch of things in here. So let's do a quick sudo apt get install nasm build essential. Let's go ahead and install this, and I'm just going to pause the video while the download and install is happening. Okay, so I think the installation was happened, including NASM and a bunch of other tools required for compiling, etc. on this platform. Now what I'm going to do is we need to upload our source code which is there in sle-code.zip into our little VM, and these are the exercise files for all the forthcoming videos, right? So let me go to VirtualBox, and right now what you would notice is that we are in NAT mode. Just going to change this real quick, and I'm going to make this bridged mode, right? Simply because I'd like an address to which I can connect to an SFTP. So if you notice, momentarily we lose connection, which is okay because the network mode is being changed. Let's give it a bit. And now we have our new connection. Let's check out our IP address. It's 0.179. You may have something entirely different. So let me do an SFTP security tube at the rate 192.168.0.179. Which looks like the SSH daemon is not running. Let me check for a second. So let's go ahead and install and run the SSH server. You can do a sudo apt cache search sshd so we know which package it's in. So it's basically inside OpenSSH server. Let's install that. Sudo apt get install OpenSSH server. Okay, now let's go back. Password is security tube in my case, and ensure that your current directory has slecode.zip. Done. Let me go back here into my VM, and if I do an ls, I can see my slecode.zip has been uploaded. Right, so let me unzip this. Now I have an SLE directory, and basically inside this there are multiple directories. The root level ones are for basic assembly, and the shellcode one is where we discuss different shell codes and all of that, right? So these are all your exercise files which you need to go ahead and have inside the VM, right? One of the other things also is that you'd want to increase the screen resolution size, etc., and this would require you to install the VirtualBox guest editions. So this would take a bit. Again, let me just quickly pause the video. Okay, the CD icon would kind of appear at the bottom, which would say VBox editions. Click on it and then run auto run.sh. Right, the password in my case is security tube. So this would take some time while all the installation is happening. I'm just pausing again for a bit, as all of this is unnecessary to just wait. Okay, it's done. Now the next time you basically restart, you would see that the resolution would be something which can increase, and that's really something. Let's quickly go ahead and try. So actually, you know what, you could do the restart in just a bit. Let me bring up the slides again. Okay, so I think we've finished NASM installation. The code files are all installed, and I think you're ready to go. There are one or two small utilities which you need to install later, like libemu, which appropriately, whenever we take it up, you can go ahead and install. So I think this should be sufficient to start off with the next set of videos. And all the best with the course. Thank you. Hello all. Welcome to exercise 1.2 for the topic what is assembly language. Now I'd requested you to find the CPU details on an Ubuntu system. The first thing was to figure out if your processor is 32-64-bit, and at the very same time to find other additional capabilities such as the presence of an FPU, MMX, SSE, SSE2, etc. Excuse me. Now you can do this using two commands. One is lscpu, and the other is by viewing the proc/cpu info file. So let me show you how to do both of these. So I'm going to my lab setup, and let me run lscpu. So if you notice, it says the architecture is i686. The CPU modes available are both 32 as well as 64-bit, and the byte ordering is little endian. This is something we'll come back to in later videos, and why this is important from the reading and storage of data in memory. Okay, we just have one CPU on this one, and a couple of other interesting things are available as well. The other command is cat proc CPU info, and this gives you a little bit more view into what is actually there. Now, if you notice this little field here called flags, this is important because this tells us a lot about the capability of the current CPU. So if you notice, it has an FPU unit and it does support MMX instructions, SSE, SSE2. LM stands for long mode, which typically means 64-bit, and it also supports other instruction sets such as the SSE3. Now we have installed this whole setup inside an Ubuntu 32-bit machine. So even though the CPU is 64-bit, it is going to go ahead and allow us to use it in a 32-bit mode, right? So these two commands allow you to quickly figure out your CPU information to give you an idea about your working environment. So that's all for this video. Thank you. Hello all, welcome to this video in which we will talk about IA32 architecture. Now before we begin, let's try and visualize a computer in the form of basic building blocks. Now if we were to do that, the first block you would build is the CPU, or the central processing unit, which is where different instructions are decoded and executed. Then we would have a memory block where our program, data, etc. gets stored. I/O devices like your monitor, LAN card, etc. And then finally a system bus which connects them all. Now let's first take up the CPU and understand that better. Now you could break up the CPU into a control unit, which is responsible for retrieving and decoding instructions. And then you have the execution unit, where actual execution of the instruction happens. Now, as you can imagine, while the CPU executes, it would require temporary storage of data, etc., which it would want to use in different computations. This is where registers come in, which you could visualize as internal memory locations inside the CPU, which act as temporary variables. Now, while different computation operations are going on, there could be different events, such as a computation leading to a zero value, and the CPU would want to indicate all of this to the programmer or to the program. And it does this by using what is called the flags register, again, which is part of the CPU. Now let's actually look at the registers in more detail, right? Now here is a logical diagram of IA32 registers, which primarily consists of the general purpose registers, the segment registers, E flags, EIP, a floating point unit, which now is pretty much integrated into the CPU, and MMX and XMM registers. Let's look at each of these to understand them better. Now, there are 8 general purpose registers. The first 4 are EAX, EBX, ECX, and EDX. Now, for IA32, as you probably already guessed, these are 32 bits wide. Now the interesting part is, even though these are 32 bits, we can go ahead and access the lower 16 bits using the AX register, which is basically nothing but a subset of EAX. Now more interestingly, we can actually break down AX further into A low, which is basically the bit 0 to bit 7, and A high, which is bit 8 to 15, which is now you've broken it up into the lower half as well as the upper half, right? So EAX itself is 32. You can break it up into AX, which is basically the lower 15 bits, which can further be broken up into AH and A low, where AH is basically 8 to 15, while A low is 0 to 7, right? Now the best part is that EBX, ECX and EDX work exactly the same, and you could actually once again break up EBX into BX, which further can be broken up into BH and BL, and same for ECX and EDX. Now the best part is that in our assembly language program we can reference not just EAX but also AX, AH, AL, BH, BL, BX and all of that, right? Which gives us a lot of freedom to play around with these registers. Now apart from these four, we have four more, which is ESP, EBP, ESI and EDI. Now unlike the first four, these can only be further broken up into the 16-bit lower half. So for ESP you have SP, for EBP it's BP, ESI it is SI and EDI it is DI, right? So these 8 are what constitute the general purpose registers on IA32. Now let's look at the common functionality for which these registers are used. EAX is called the accumulator register and typically is used for storing operands and result data from different calls such as syscalls, etc. EBX is the base register and more often than not points to data. ECX is used in loops and is aptly called the counter register. EDX again is a data or an IO pointer. ESI and EDI basically again are typically used as data pointer registers for memory locations. When we will look at string manipulation in assembly, we will actually use ESI and EDI along with the direction flag. ESP or the stack pointer register. Now keep in mind, among all the general purpose registers, ESP is probably the only one which we would not go ahead and arbitrarily use for any purpose. ESP is specifically used just for stack manipulation. Now if you do not know what a stack is, what it stands for, etc., don't worry, we will cover that in a later video. Finally, EBP, which again is actually used as a data pointer register. Now apart from these 8 general purpose registers, you also have segment registers, which are CS, DS, SS, ES, FS and GS. Now CS is code segment, data segment for DS, SS is stack segment, and ES, FS and GS again point to different data segments. Now the usage of these registers, the segment registers, depends very much on the memory model we are adopting. So their usage would be very different if we had taken a flat memory model versus a segmented memory model. Again, if the different memory models is something new to you, don't worry, we will cover this in the next video. Now apart from these, you basically have the flags register, which are used to indicate different things happening in the CPU, right? So as an example, if an instruction leads to a 0 value, then the 0 flag gets set. We will take up the flags register in more detail when we look at conditional statements in assembly language. Apart from this, you have EIP, which is basically the holy grail for shell coding and for exploit research, and that contains the instruction pointer, which is basically the next instruction to be executed. EIP is 32 bits wide. The segment registers though are just 16 bits wide. Now apart from this, you also have the floating point unit, or the x87 as it is called. Now the floating point unit has different data registers for manipulating floating point numbers, and the size of these registers is 80 bits. These are named ST0 to ST7, and interestingly, these data registers behave like a stack. We'll take up more details on FPU, ST0 to ST7, etc. when we take up FPU later on while programming in assembly. Now, apart from this, Intel basically came up with a lot of other extensions to their instruction set. SIMD, or single instruction multiple data, was one of the main enhancements done by Intel, and these instruction extensions include the MMX instruction set, SSE, SSE2 and SSE3. Now these extension instruction sets use MMX and XMM registers. Now what are these registers? Well, MMX is actually carved out of the FPU registers. So if you remember, I had mentioned that the FPU registers are 80 bits wide. Well, the first lower 64 bits is what is assigned to the MMX registers. So MM0 would basically be 0 to 64, 0 to 63 bits, and so on and so forth to MM7. XMM is actually an even bigger register, and it is actually 128 bits in size, and you have XMM0 to XMM7, which is 8 XMM registers are available. Now we will look at some of these registers when we look at more advanced assembly language programming in later videos, right? In this video, all I wanted to do was introduce you to the different registers, and now coming to the lab exercise, what I would like you to do is inspect the general purpose segment, FPU, MMX and XMM registers on your Ubuntu system. Look at the values they hold. As far as general purpose registers go, see if you can look at the lower 16 bits separately, like AX, or even further, which is AH and AL, etc. So that's all for this video. Thank you. Hello all. So in the theory class, what we talked about was the different general purpose registers, segment registers, E flags, FPU, MMX and all of that. But now the question arises, how do you look at all of these CPU registers, right? So to do this exercise, let's log on to our Ubuntu system. And here's the thing, right? While your system is running, the only way you can analyze CPU registers is in the context of a running program. And for this, we require a program such as a debugger, which can help us kind of matrix style pause and freeze our program. And in that frozen state, allowing us to analyze CPU registers, etc. Now on Linux, GDB or the GNU debugger is the de facto debugging tool which is available. Now I also have a related series on GDB. I'll probably post the link when we just start the assembly instruction set, and at that time you can go ahead and look at GDB in more depth. Anyway, so what we are going to do is let's pick up one of the programs on the system. So let's pick up bin bash and run GDB on it. So we say GDB bin bash, and this is going to load up GDB for analysis with bash. Now let's create a breakpoint for the main function and let's run the program. And as you notice, we've hit our breakpoint. Right now, if you've never programmed before, have no clue, this doesn't make any sense, don't worry. In a later video, I'm going to point you to GDB and where to pick up all the basics, right? Okay, now to look at the CPU registers, we are going to use info registers. Now, if you notice on the left hand side, this has the register name such as EAX, and then here you have the value inside the register, right? This is the hex equivalent. And if you notice, all CPU registers are listed here. Now, there are a bunch of things which you probably want to look at. And for that, let's go back to our slides. And if I quickly go back here and just put this in context of the CPU registers, you would remember I had said that each of these can be broken up into further 16-bit registers. So EAX actually can have AX, which is accessible separately. So if we go here, and now one of the ways in which you can print the contents of the register is to use the display command, and dollar is prepended before the register name, and if you notice it gives you the value 1. And now if I wanted to print AX, which is the lower 16 bits, then I'm going to do $AX, and you would notice it prints the value 1. Now, which is of course going to be true because 0, 1 is nothing but 0, 0, 0, 0, 0, 0, 0, 1, right? Now, if you did the same thing, let's say for the ECX register, we could print ECX, which is the whole value. And now if you just wanted to print CX, which is the lower 16 bits, you would actually find that this value, which is F3, F4, is what got printed, right? Now, you could play along a little bit in that direction by, let's say, now printing CH and CL separately. So we could basically do CH, and as you're probably already predicting, the value which needs to come out needs to be F3. And then we're going to do CL, which is going to be 0 to 8 bits of the ECX register, which would be F4. And there you go, right? Now, you can try out a couple of others on your own. But basically what we observed for the general purpose registers is either you can access all the 32 bits or selectively the lower 16 or 0 to 8, 0 to 7 and 7 to 15, which is the lower byte and the higher byte, right? AH and AL. Same is in the case of ESP, where as I mentioned, you can go ahead EBP, assign EDI, where you can go ahead and basically get the lower half or the upper half. Now segment registers. So if we go back here, you notice our segment registers are all mentioned here. CS, SS, DS, ES, FS, and GS. Fantastic. And they contain, different values depending, as we said, on the memory access schema which is going to be used. Linux basically uses protected mode and flat memory models, which we will visit in a later video. And then after that you have the E flags. And if you remember, if we kind of go to the flags theory part here, you would actually notice there are different flags like ZF0 flag, SF sign flag, and all of that. Now, when you basically look at E flags, here is the value. You can convert this into individual bits and then compare it with the whole bit mask, which is there in E flags, to figure out which one is enabled or which one isn't. GDB makes this easy for you by specifically mentioning the flags which are enabled. So ZF, the 0 flag, is enabled. Now, if you look at PF, and if you kind of go back again to the slides, what you would really notice is PF is nothing but the parity flag, which is also enabled. ZF is enabled. And similarly, a couple of other flags are enabled as well, right? So this is how we can look at the E flags. So we've looked at basically the general purpose registers. We've looked at the segment registers. We've looked at E flags. Now EIP, which is the next instruction to be executed, is inside the EIP register. Now, in order to look at what is the next instruction, you can use the disassemble command. Go back here, just print info registers. We can use the disassemble command, and then we can tell it where to start disassembling. And at this point, this is what $EIP actually contains, which you could verify very, very quickly by running info registers. And here, if you notice, this is the value, which is exactly what we have here, right? Awesome. Now, depending on which Linux system you're running and facts that there are multiple mechanisms enabled, excuse me, for program relocation like ASLR and all of that, you may find that these values may change between invocations and all of that. So let's not worry of the absolute values. You may have a totally different value when you're running this on your machine. So keep that in mind. Now let's look at the other interesting registers which we wanted to look at. FPU. Now interestingly, we have FPU, we have the MMX and the XMMs, and when we actually do info registers, oops, you notice it's not shown, right? So by default, GDB does not show you floating point registers, MMX and XMM, sorry. Now to have GDB show you all of those registers, we use a command called info all dash registers. And if you notice, we have our general purpose registers up here, we have EIP in here, we have E flags in here, we have the segment registers, and from that point on, if you notice, we have ST0 to ST7, which we had kind of spoken about, is basically the FPU data register stack. And if you go further down, you would actually find that we actually have our XMM0 to XMM7, and then after that you have your MMM0 to MMM7, right? This is where your MMX and your XMM registers are present. Fantastic. So keep that in mind. Later on, when we start playing around with programs, we will use GDB extensively to monitor what the program is doing, how the registers are changing. And as far as shell coding and all of this is concerned, exploit research on Linux, you have to have a command over GDB. It is the de facto debugger you can use on this platform, right? And probably the best option available to you, absolutely free of charge. Now, one of the things which I wanted to pick up, which I'll talk about later as well, is when we do the disassembly, the assembly language on the right hand side, right, can be shown in two different modes. One is called AT&T, two different syntaxes actually, and the other is Intel. Now the default on Linux is basically the AT&T syntax. Now in the whole of this course we will be using Intel syntax, and there's a very easy way by which you can tell GDB to change everything to Intel syntax rather than the default AT&T one, which is set disassembly flavor Intel. This is the command, and once you do it and you disassemble, now you have everything in the Intel syntax, right? I'll come to what Intel syntax is and what all of these kind of jumbled things on the right hand side mean in later videos, but keep that small thing in mind about GDB, which we will use later on, right? Fantastic. So that's all I had in mind for this lab exercise, right? And what we've basically done is we've located all the different registers, general purpose, segment, E flags, EIP, FPU, the MMX and the XMM ones, and so that when we write code to leverage those registers, then we can use tools like GDB to monitor what is happening. Fantastic. So that is all for this video. Thank you. Hello all, welcome to video 3, and in this video we will talk about CPU modes and memory management. Now IA32 has 3 modes of operation. The first one is what is called real mode. Now the processor is in real mode by default whenever it is powered up or it is reset. Now the problem with real mode is that in that specific mode it can only access up to 1 MB of memory, nothing more. And there can be no memory protection or privilege level such as differentiation between kernel and user space be applied to the entire system. The second mode is what is called protected mode. And in protected mode, the processor can access up to 4 gigs of memory. And memory protection, privilege levels, multitasking, etc. is possible. Now, this also has a special virtual 8086 mode to go ahead and execute softwares which are kind of outdated from the previous generation. Now, the third mode is the system management mode, which is typically used for power management tasks and couple of security related tasks. Now, as far as this entire series is concerned, we will only be concerned with protected mode, right? And pretty much as far as real mode, SMM, and even virtual 8086 mode is concerned, if you want to look it up, you can check out other websites or the Intel manual. But we will focus only on protected mode because this is what almost all modern operating systems use, including Linux, of course. Now, apart from the CPU models, as you can probably imagine, memory modeling is also very, very important, right? How does the processor go ahead and address the memory? Now, this is where basically there are three options. The first is flat memory model, in which the address is pretty much linear across an address space, and you can access any of these addresses directly, right? The second is segmented model, in which you basically use a segment selector and an offset in that segment to go ahead and figure out how to access specific locations. And then finally, you have real address mode model, which is basically a special case of the segmented model. Now, again, for all purposes of this video series, we will only look at flat model. Now, you're probably asking why I made both of these two choices. This is because IA32 Linux basically uses protected mode and a flat memory model for functioning, right? And this is all we are going to look at. And during this functioning, it has up to 4 gigs of addressable space. And as we've mentioned, memory protection, privilege levels, multitasking is possible. Now, the segment registers, which we spoke about in the previous video, as far as in protected mode, flat memory model is concerned, actually point to something called segment descriptors. Which could either be the GDT, LDT, and IDT, which stand for global, local, and interrupt descriptor tables. Now, we may not have to look into too much of this just for a pure assembly and shell coding series. Maybe later on, when we look at more interesting stuff such as malware, reversing, and all of that, we could look at GDT, LDT, and IDT. Or if you're interested in writing your own operating system. Okay, so what we spoke about in the last couple of slides was basically the fact that we can access up to 4 gigs of memory, right? Now, what does this mean for any process running on a 32-bit Linux system? Well, this is where virtual memory modeling comes into picture. Now, virtual memory model allows a process to think that it basically is the only process on the system which actually occupies the entire 4 gig of space, right? And this 4 gig is divided into 1 gig, which actually belongs to the kernel for various important things it requires. And then 3 gigs is user space, which is where the processes, code, and all of those things are loaded. Now, if I break this up further, this is how it would look like, where typically you would actually have the process program code loaded inside a segment called the text segment or the text section. You would have all the initialized data, which is data you go ahead and specifically initialize. For example, you initialize a password or you initialize an array of numbers. All of those are stored in the data segment. Then you have BSS, which is where all the uninitialized data gets stored. Now, apart from this, you have the heap, which is responsible for dynamic memory allocation. We could go ahead and map shared libraries and even shared files and things like that into the process. And of course, we would also have something called the stack, which is where function arguments, local variables, and all of that get stored, right? And then finally, you have the kernel space, which extends to the last 1 gig of memory. Now, the important thing is that once you have this structure in your mind, it's going to be very, very easy to understand how all of these things play together, right? Now let's go ahead and look at a real example. Now, I've actually said this is how a process would look like in memory, right? Now, is it possible for us to go ahead and actually see a real process and how it's laid out? Well, to look at process organization in memory, there are multiple ways. If your system supports proc, then proc PID maps gives you how this program memory actually looks like or how it is mapped. Pmap is also another utility which allows you to do the same thing. And then finally, we could also use GDB to attach to a process and view how it is laid out in memory. So let's go ahead and do all of these three. So let me go into my Linux box, and in the very first example, let's actually look at our own memory, right? So basically what I can actually do is pick up the PID and actually do a cat proc and then paste the PID. Remember, you need to be root if you want to look at processes owned by some other user. And then basically we have maps. And if you notice, this gives us a huge dump of how the process is actually laid out in memory, right? And you would actually notice that we start at this exact offset, which is 08048000, which is typical for processes loaded on Linux. And then you see a bunch of things here, right? So what do all of these things mean? Let's go back to the slides. And let me break this up for you. Now, the first two things which you see is nothing but the start and end address of the section which we are looking at. The next four values give you an understanding about the permissions of that section. Now, permissions include read, write, execute, and as far as the last value is concerned, this can either be a P, which is this is private and not shared, or an S, which is this segment is actually shared. Now, depending on whether this was mapped from a file, right, the next value is nothing but the offset inside the file for the memory mapped file. Now, in case it is not mapped from a file, this is actually set to the value 0. After that, you have the major and minor device number of the device from where the file was loaded, and then you actually have the inode number for the file, and finally you have the file path if that is applicable. So with this, if we go back here, what you would actually notice is this is the start and end address of this specific segment. This has read enabled, execute, and this is private. Offset starts at 0. This is mapped from the file bin bash. This is the inode number. This is the major minor number of the device, right? And if you look at the next segment, you would notice that the offset actually changes, right? So as the third segment. Now, apart from this, we talked about other things which could be there, such as the heap. And if you scroll down, you have the stack, which we spoke about, which is in high memory, and VDSO. So VDSO basically is used as a much more intelligent way to do syscalls. We'll probably look at this later on when we look at system calls. Then in between, you have shared libraries which get loaded up, right? You can clearly see you have libc here, And then you also have a couple of sections which aren't named anything. Uh, these are called anonymous sections, right? And typically correspond to sections loaded by mmap. So this is how the process looks like when it is loaded into memory. Now, another way you could go ahead and find this out, uh, is basically by going ahead and running this inside GDB, right? And to do that, we would load up the process and basically use the command info proc mappings. So let's actually go back here and let me load up bin bash. And if I actually do an info proc mappings, you would notice it basically says no current process is actually running. So let's run this. Let's actually go ahead and hit a breakpoint for main, run the process, hit the breakpoint. Now if we do an info proc mappings, you would notice that we can see the mapping similar to what we've seen in the previous output, right? One of the other ways to do this is to use a little command called pmap, and you could use to figure out the PID, pmap-d 5544, and you would actually see the mapping here once again. Now notice the anonymous sections are actually marked accordingly rather than just being left blank as in the previous outputs, right? So this is exactly how you can figure out a process's mapping. You can play around with pmap, more of GDB commands and all of that stuff. So the real thing which I wanted to touch upon is now you understand how a process is loaded and how it looks like in memory, right? Fantastic. That's all for this video. Thank you. Hello all, welcome to part 4 of the SLAE course, and in this video we will finally look at a Hello World program and how you can code it up in assembly. Now before we move into all of that, one needs to understand the different instruction sets available for IA32. So you first have the general purpose instruction set, which typically uses the general purpose registers and the E flags. Then you have the x87 FPU instruction set, which is anything you want to do with floating point numbers, you could basically use this instruction set. After that, you have the extensions, which include MMX, SSE, SSE2, SSE3, SSE4, and anything Intel decides to come out with later as an extension. Now, we've seen in the very first video that to go ahead and create the final machine language code, we need to take an assembly file and use an assembler linker combination to convert it into machine code which the CPU can understand. Now, this is done using NASM and LD in our case. NASM is an assembler called the NetWide assembler. It's free open source. You can download it from the link below. I've already shown you how to install NASM on Ubuntu in an earlier video, so you should already have it. And LD is basically the linker which links the object files, shared libraries, anything you would need to go ahead and finally create the executable. The executable which we will create is in the ELF format, which is the most common format on Linux-based systems. Okay, so in order to create a Hello World program, what exactly do we need to do? So as I mentioned to you previously in the last video, all the program code needs to be inside what is called a text section. So let me actually go ahead and let's type all of this together, right? So let's create a file called hello world.asm. Right, and I'm going to use Vim. You can use any text editor you are comfortable with on Linux, such as Pico or anything else for that matter. Now, in order to go ahead and enter a comment, we can basically go ahead and use this character and then say hello world.asm. Right, you can type in your name, author, and now we come to the main meat of the program. Now, as I mentioned, the very first thing we want to do is mention a text section, and the way you can do that is by entering section, and then you can actually mention that this is the text section. Fantastic. Let's go back to the slides. Now, in the hello world program, as you imagine, we want to mention the string hello world somewhere, and this would have to be in the data section where all the initialized data is put in. So now let's go back and mention the data section. Let's do it down below. So we say section, and then we can actually go ahead and say dot data. Now inside the data section, you want to mention the hello world string. So let's go back to our program, and here is where I introduce you to something called a label, right? So what we are going to do is the message we want to print, hit a tab, you could ignore that if you like, message colon, and now we want to go ahead and basically put our string hello world inside the data section. Now to do that, you could actually use something called db or define byte, with which we can define a series of bytes or even an individual byte, and this is something NASM understands, right? And we can actually say after that hello world with our exclamation, and here goes, right? So this is how we are going to go ahead and define hello world string inside the data section. Note that this is inside the data section, and we are identifying the hello world string with the label message, which we will later on use in the program. Let's go back to our slides. Now that we have defined all of these sections, the next logical step, as you can imagine, we have a text section which can contain procedures, which can contain a lot of code. So it is important to be able to tell, the linker where the entry point of the program is actually going to be. And this is where we are going to identify the entry point using the _start identifier. So let me actually go back here, and I'm going to go inside the text section and basically put in _start, which kind of identifies where the program entry point is going to be. And I would need to go ahead and mention this up on top as well, which actually would say use the global identifier, and this basically says, hey, we are going to use _start as the entry point, right? Fantastic. Now let's go ahead, come back in here, and now comes in the next part where we need to figure out how to print to screen and how to exit gracefully, right? So we want to print hello world to the screen. Okay, now this is where we need to understand a little bit more about how all of this works. Now, as far as printing to screen is concerned, you could manage somehow to use all the low-level features of interfacing with hardware and all of that. But as you can imagine, that is not something which you would like to do. Instead, you would like to leverage the operating system for more complicated tasks. And when I mean more complicated tasks, it would be, for example, writing to disk, printing on screen, interfacing with certain devices, and things like that, where writing code from scratch could really be very, very cumbersome, right? This is where system calls come in. Now, system calls provide a very simple interface for user space programs to request the kernel to do complicated tasks for them. Now, how do system calls work, right? Now, a user space program calls a system call, and once that is done, so as an example, one way of invoking system calls is to generate an interrupt 0x80. Once that interrupt is generated, the CPU will go ahead and check the interrupt handler table and invoke the system call handler. Now, once this is done, the system call handler basically is a kernel mode program. And this system call handler goes ahead and figures out the specific system call routine we are interested in. So as an example, if you want to write to the screen, there is a specific system call for that. If you would like to go ahead and read something from input, that's basically a separate system call, right? Now, where are all of these system calls mentioned? I'll come to that in just a bit. But before that, there are multiple ways by which you can invoke these system calls in user space programs. On IA32, you can do this by using interrupt 0x80 or the sysenter instruction. It's important to note here that modern implementations typically use something called VDSO or Virtual Dynamic Shared Object, which is a more efficient way of doing system calls. Now, how VDSO works and all of that is probably beyond what I could cover in this course, simply because it requires you to understand more about how the kernel functions, how the loader works, and a bunch of other things. However, if you're interested, you could refer to the link below and understand how system call is actually implemented in the kernel. Now, from our perspective, which is pure security, shell coding, and all of that, we would almost exclusively look at interrupt 0x80 for whatever we do with respect to system calls. Okay, so we said that there are so many system calls which may be available. The next logical question arises, where are these system calls defined, right? So let me open up a new terminal. And I'm going to open up the file user include i386 Linux GNU. And remember, if you use a different system, the location would be different. And then after that, you have a bunch of files in here. The one we are interested in is the 32-bit one, which is unisted_32.h. And this mentions the full list of system calls which are available to you, right? There are many system calls, as you can clearly see. System calls to create directories, to change directories, to make nodes, to unlink files, to go ahead, open, read, write, and whatnot, to restart the system, to exit a program, to fork a new process. Practically all the low-level stuff which you would want the operating system to do is all mentioned in the form of system calls. And this is of huge importance to us. Okay, let's come back. Let's go back to the slides. Now, we go back to what we really wanted to do, which is print to the screen and then exit the program gracefully, right? And this is where we need to use appropriate system calls to do both of this. Now, to write to a screen, we basically want to use the write system call. right? And the write system call is basically identified with the syscall number 4, and you would actually have a wrapper on it, which you can figure out via the documentation using man to write. And if you read through the documentation, you can invoke write. The first input is actually going to be a file descriptor. The second input is going to be the buffer, which actually contains what you want to write into this file. And then finally is the length of what you want to write, right? Now, in our case, we want to write to std out. Now, for any program, by default, std in, or the input, is mapped to file descriptor 0, std out is mapped to 1, and std error is mapped to 2. So in our case, the value of fd is going to be 1. Now, buffer or buff actually would be pointing to the hello world string which we have. And finally, count is nothing but the length of the hello world string. Right? Fantastic. Let's go back to the slides. Similarly, exit just requires us to give an exit status. Typically, the value 0 is used to indicate that the program exited without any problems. If you give a non-zero value, that may have an indication that the program had certain issues while exiting. Now, the question arises, we have all of these inputs which need to be fed into the system call, right? How do you pass all of these inputs before invoking a system call? Now, this is where for IA32, you are going to go ahead and pass these via registers. Now, the EAX register must contain the system call number. If you remember, we found out that for write, the value of this number is 4. EBX, ECX, EDX, ESI, and EDI would contain the first, second, third, fourth, and fifth argument, depending on the number of arguments, right? If you have more than that, the ideal way would be to pass them in the form of structures. Now, once the system call returns, because every system call would typically have some sort of a return value, the return value is pretty much put always inside the EAX register. This is important if you would like to use the return value of the system call further in the program. Now, to elaborate on that, basically EAX register would contain the system call number. EBX would basically contain what int fd should be, and as we figured, that would be std out, and the value for that is actually 1. After that, ECX would actually point to the hello world string, and EDX would have to contain the length of the hello world string which we want to print. So let's go ahead and set all of this up in our little program here. So what we mentioned was that the EAX register would have to contain the syscall number, and what we located that for write the value is 4. So move EAX the value 4, right? You could also mention 0x4 in hex, but remember, either use hex or use decimal, don't mix up both. So let's just use hex. Now, then we said EBX basically would contain std out, which is 1. So EBX would be 1. And the move instruction, we'll take this up a little later in more detail, is responsible for moving data into registers, between registers, and memory location and all of that. So the way move works is, this is the destination and this is the source. So move EAX, 0x4 moves the value 4 into the EAX register. Move EBX 0x1 moves the value 1 into the EBX register, right? so on and so forth. Now the third thing which we said is ECX would actually have to contain the pointer pointing to the hello world instruction. Now the interesting part is we can reference the hello world string with just the message label. So move ECX would actually comma message would actually move the address of the hello world hello world string into ECX. After that, we want to move the length of the hello world instruction, which we can do basically as a first iteration by counting it, which would be 1 2 3 4 5 6 7 8 9 10 11 and 12. This is one way of doing it, and you could put in the value basically 12 in here. Alternately, there's a quick shortcut which you can actually use, which NASM understands. You can say message length equals dollar minus message and this would basically have mlen in here. Right, so this automatically computes the message length for us. Awesome. And then after all of this, as I mentioned, we need to go ahead and issue the system call, which is done by issuing via interrupt 0x80. So this is basically going to go ahead and print hello world on the screen. Now the next step is actually to exit the program gracefully. Exit the program gracefully. And kind of go back here, the call to exit. So the first thing is to find the system call number for exit, and then to find the status code which we want to return inside EBX. So if we go back here, exit basically is system call number 1, so it should actually mean move EAX 0x1, and then move EBX. Let's say we want to return the value 5, and then we basically enter 0x80 to issue the syscall, right? So this is how we are able to now create a very simple program. Now let's go ahead and assemble and link this. So let's use NASM. The -f option is basically the executable format which you want to create. In our case, it's ELF32. And then basically we mention the output file, which would be hello world.o, the object file, and this is the input file. And basically if we kind of go ahead and look at the instruction here, I think I made one little mistake. You have EQU for equal. There you go. So now basically you notice that we have an object file hello world.o, and what we need to do next is basically link this into an executable ELF format. So you're going to say hello world, and here is the object file, right? So now we have a hello world executable inside the same directory. Let's run it, and it printed hello world. Fantastic. And if you want to look at the return value of the program, you could just do an echo $? And if you notice, the return value was 5, which is exactly what we had given in the program, right? Chose the value 5. Awesome. So this is how we can create a very simple assembly language program to print hello world on IA32 Linux. And pretty much this whole format of writing an application file is exactly what we'll use in later videos as well. Now comes the exercise, right? Now we went ahead and created this hello world program, and the program kind of executed and we were able to see the output. However, what about analyzing and visualizing all those micro instructions such as move EAX, 0, move EBX1 and things like that? How do we go ahead and look at all of that at a microscopic level? This is where GDB comes in, and the exercise associated with this video is that use GDB to step through the hello world program, observe the CPU registers, see how data is being transferred, look at memory locations, and a bunch of other things, right? So that's all for this video. Thank you. Welcome back. Now in this exercise, we will look at how to use GDB and step through the hello world program and observe things like CPU registers, memory locations, etc. So let's go to our setup, and you should find the hello world.asm.o, which is the object file, and hello world, which is the binary. Now let's load up the hello world binary in GDB. And in order to go ahead and pause the execution of the binary, we need to set a breakpoint. So let's go ahead and set a breakpoint for _start, which you remember was what was defined as the entry point into the program. And now let's run the program. As soon as the program was run, we've hit the breakpoint at _start. Now if you want to disassemble code, let's use the disassemble command. Now what you may notice on the right hand side is assembly language, of course, but something which looks different. Now in assembly language, you typically have two kinds of syntax. One is called the AT&T and the other is Intel syntax. Now AT&T kind of was the native syntax for Linux, where GAS or the GNU assembler and all of that use that. However, we are interested in using only the Intel syntax because when we go to Windows assembly, you would see that pretty much all the tools, output, etc. use the Intel syntax exclusively. So the idea is to be coherent. As far as Intel and AT&T is concerned, you could practically write the exact same instructions in these two different representations. I'll touch upon the differences between AT&T and Intel at the fag end of this course. Anyway, so this isn't useful to us because it's in AT&T syntax. So we would like to see the disassembled output in Intel syntax. To do that, you can actually set the disassembly flavor to Intel. Once you do this and hit disassemble, you should see our familiar AT&T syntax coming back. Right? Fantastic. Now, if you remember this part of the code, this is nothing but going ahead and printing hello world on the screen, and this is the part where we exit gracefully, right? Awesome. Now let's go ahead and step through this program and look at how the registers change. So in order to look at the CPU registers, we use the info registers command, and this basically shows us the current register state. If you notice, currently EAX has the value 0 in it. Now let's step through these instructions. If you look at the left hand side, this little arrow points to the next instruction to be executed. To step through the instructions one after the other, we use step I. And now when we hit disassemble, you would notice that this instruction has been executed and this is the next instruction to be executed. Now, before this instruction was executed, the value of EAX, as we can see, was 0, and this should move the value 4 into the EAX register. So an info registers would actually show us that the value 4 was moved inside EAX. Now at this point, the register EBX has the value 0 in it. The next instruction should move the value 1 inside it. So let's do a step I. Look at the registers again, and you would notice that EBX currently has the value 1 in it. Fantastic. The next instruction would load a large value 0x804990A4 inside ECX. Now, if we were to compare this with the source code, right? So let me open up another terminal. You would remember that in ECX what we were moving is the memory address where hello world is located, right? And looks like this seems to be the address where it is located. So we could copy this, and if you want to look at this, you can use the x/s command, which is going to examine memory but print this location as a string, and you would notice that we have hello world in here, right? Fantastic. Now the point to remember is we specifically did not null terminate hello world. In this case, it was null terminated because probably the next couple of values were zeroed out, but keep that in mind. Okay, so this is going to be moved inside EAX in the next command. Let's run the next command, look at the registers again, and as sure as it should be, that value has been now loaded into ECX. Similarly, the value C would be loaded into EDX, which currently is 0 when we run the next command. And as you notice, the value C, which is nothing but decimal 12, is loaded into EDX. And the very next command is actually to generate the system call by going ahead and initiating interrupt 0x80. So when we do a step I on that, you would notice that hello world got printed as expected, and now we are in the next instruction. Now at this point, if we look at the register state, what you would actually notice is that the register EAX has a value 12 inside this, which is the return value of the write system call which we called. And from what I remember, write basically returns the number of bytes which it has written, and which is nothing but again the string length of hello world, which is 12, right? So this was returned inside the EAX register. Fantastic. Now the next instruction is going to put the value 1 inside EAX, which it did. The instruction after that would put the value 5, which is the return code for exit inside EBX. Right? Don't care about any of the other registers, and we generate the interrupt in the next step, which is we are about to generate it. And once this is generated, the program exits gracefully. And as you can see, GDB tells you that process 2180, which was running, has exited. However, the exit code is 05. Fantastic, which is what the exit code we had loaded. Awesome. So this is how we can trace through a program, look at the CPU register state at every point from within GDB and understand what is happening, right? In the beginning, I would really recommend using this technique to understand how each and every operation works in assembly language. That's all for this video. Thank you. Hello all, welcome to this video on data types. So as far as the IA32 architecture goes, the fundamental data types include byte, which is 8 bits, word, which is 16, a double word, which is 32, quad word, which is 64, and as you probably already guessed, double quad word, which is 128. Now, in each of these cases, you have the notion of signed and unsigned. Now, in the case of unsigned, well, the whole 32 bits, as in the example of an unsigned double word, is dedicated to storing the value. In the case of a signed double word, 31 bits are dedicated to storing the value, while the last bit, the most significant one, is used to store the sign, which can be positive or negative, right? Now, before we move into more assembly language, there are a couple of things you need to know about NASM, which is the assembler we will use for this entire series. Now, NASM is case sensitive, and what this really means is you need to be very observant about naming your labels. The second thing is that accessing memory has a very simple way to be done in NASM in comparison to many other assemblers. So let me give you an example, and this is something you could correlate with the previous Hello World program we just wrote. So let's say we define message with db, which is defined byte, as a sequence of 4 bytes, AA, BB, CC, and DD. When we type in move EAX message, this actually moves in the address of where these 4 bytes are located into the EAX register. Now, if you actually want to go ahead and move these 4 values, then you need to reference the address using the square brackets. So move EAX message with the square brackets actually moves the value referenced by message into the register. A little typo, it's move, the E shouldn't be there. So this is an important concept. Now, we've talked about data, right? And you have initialized data, and then you have uninitialized data, right? So in NASM, you can define initialized data using a bunch of pseudo instructions such as db, dw, dd, dq, dt, etc., depending on the data type you're interested in. Now, db is defined bytes, where you can define individual bytes or a sequence of bytes. You could even use character constants in them, or even strings for that matter, as we've seen in the Hello World program. Now, the key thing you need to remember is byte is basically just for one single byte, while word is for 2. So as an example, if you do a define word and just use A as the character, then in reality, this actually translates to 0x61. 61 stands for the ASCII value of small a, and then 00, right? This ensures that the whole word is actually occupied. And this applies to every other data type in question. Now, in order to declare uninitialized data, the two most popular instructions are resb and resw. Res stands for reserve, B is for byte, and W is for word. The first instruction, resb64, reserves 64 bytes, and resw1 reserves a single word. Now, as you've already encountered in a previous video, uninitialized data is placed in the BSS segment. Now, all of this is actually present in the NASM manual from where I've picked this up. So I would recommend going through the manual, and this specific data types is covered in page 30. Apart from this, there are two special tokens which are used a lot when dealing with NASM. The first is a dollar sign, which evaluates to the current line, and double dollar, which evaluates to the beginning of the current section. Now, these are used at times to figure out the offset of the current instruction from something else most of the time. So let me give you an example of how to use dollar. Now you may remember in the Hello World program, we defined message with DB, Hello World, and in the very next line we said message length equals dollar minus message. Now let's try and interpret what this means. Now I said dollar evaluates to the current line, which means dollar actually signifies a reference to the beginning of this line right here, which is basically the end of this line, while message references the beginning of the hello world string. So dollar minus message definitely would mean the string length which stretches from H to D. And that is how we are able to compute the string length using dollar minus message. Now dollar sometimes, as you'll also read in the manual, is used to create infinite loops like jump dollar, which basically would mean it just keep coming back to the same location. Now, apart from equals, times is also another interesting instruction which we use. Times is nothing but replication of one instruction multiple times, and it can apply to both data as well as instruction. What do I mean by that? Well, let's look at this definition. 0 buff is the label, and then you have times 64 db0, right? What this means is repeat db0 64 times. In a similar way, when we look at instructions and we write times 100 move SB, this just means move SB needs to be replicated 100 times. Okay, now we've looked at some data types and how to use them in NASM. Now let's look at how data actually gets stored in memory. And this is where IA32 uses what is called a little EDN format. Now, if you've never heard about EDNS, little and big and all of that stuff, go ahead and have a look at the EDNS page on Wikipedia. Now, what does this really mean for us? All little EDNS means is the lower byte would get stored in lower memory while higher byte would get stored in higher memory. So as an example, let's say this register, which is 32 bits wide, has the value 0A, 0B, 0C and 0D in it. And you are now using an instruction to store this value into memory. On a little EDN architecture, what would happen is 0D would get stored in low memory, 0C in the next byte, which is A plus 1 if 0D was A, 0B would be in A plus 2, while 0A would be in A plus 3, right? This is very, very important because when you read memory, you need to ensure that you respect little EDNS while going ahead and figuring things out about the data which is stored. Now, we are going to be using GDB quite a lot in this entire series, and my recommendation would be to master GDB at some level. Of course, like all security tube courses, we don't like to leave you in the lurch by saying go figure this out yourself. And this is where I've already created the Security Tube GNU Debugger Expert course and certification. And all the videos for that course are included with the SLAE absolutely free of charge. So inside your course folder, there would actually be another folder which would say SGDE. Click on that, view all of those videos if you've never used GDB. It starts from the very basics so that you can understand how to use this fantastic tool to our advantage. Okay, so having said that, now let's go on to the exercise for this specific video. Here we are. Now, what I've actually done is basically gone ahead and modified the hello world.asm file and created a new file called datatypes.nasm. Right? All of this should be in your course folder. Now, typically, most of the times when you use nasm, you basically give the suffix nasm to the file rather than asm, right? Which is what we're going to do from now on. So data types.nasm typically looks exactly what you've seen in the previous video for hello world, which is all the print routine and everything remains the same. I haven't touched it. The only thing I have done is I have modified the data section and I have added a new BSS section. So let me explain. Now in the data section, you can probably recall that message and mlen are exactly what was there in the previous hello world video. That is totally untouched. Now what I've done is I've defined 6 variables in the data section and marked them with labels var1, var2, so on and so forth up to var6. Now var1 is nothing but a byte AA, var2 is a sequence of bytes BB, CC and DD, var3 is a word EE, and if you recall this should actually be EE00, and after that you actually have DD, which is for 4 bytes, and then a couple of other variations. var6 is going to be using times to its advantage, times 6 db0xff, and then we move on to a new section which we have defined for uninitialized data, which is BSS, where we've defined var7 as basically reserve byte 100 and var8 as reserve word 20. Now, one of the other things I've also done just to make our life a little bit comfortable is a simple shell script which will go ahead and assemble with nasm and then link with LD and give us the output. So to do this, all we now do is hit compile .sh and then basically just give the name of the program. Drop the .nasm when you feed it to compile.sh. There you go, it says assembling linking done. Please note I'm not doing any error checks, so if there are errors it will show up as far as compile.sh is concerned, in your case if you make any typos. Now what I'm going to do is let me run data types, and as expected it just prints hello world and exits, right? All the other variables we defined are pretty much unused at this point. Now let's go ahead and load this up in GDB and figure out what is happening. Right, we can use the -q option to load GDB silently so that we don't see all of those huge messages about the version, etc. Now there are a couple of things we need to do. We need to first set up a breakpoint so that we can look at all of this data. Now to set a breakpoint, let's say if you don't have any info about the binary, one of the ways to look at the different functions which are available. In this case, we can clearly see _start listed here, right? Now, in case you don't have this and you want to know the entry point of a given executable, right, or given ELF executable rather, then one of the things you can do is use different programs available on the Linux system to figure out the entry point. So, as an example, I could actually invoke a shell command from within GDB using shell, and then the command would be read elf -h is to print all the headers and then to give it the binary data types. And if you notice, this actually gives me the elf header. The most important field in here is the entry point address, which is 8048080, which if you look here is exactly that of the _start position, right? Now what we're going to do is let's put up a breakpoint here for _start. And if you've been following previous videos, we need to set disassembly flavor to Intel. You can also figure out how to write GDB initialization script so that all of this set disassembly, flavor, etc. is fed into GDB when it starts, so you don't have to do it every single time. I leave that an exercise to you. Now let's run this program. We've hit our breakpoint. We hit disassemble, but the thing is, disassemble is only going to show you all the instructions. It has nothing to do with data, right? So let's actually use info variables to look at all the data available to us. And as expected, it prints out var 1, 2, 3, 4, 5, 6, message 7 and 8 along with their specific locations, right? So what we're going to do is, let's open up another terminal where we can basically monitor our programs. Right, and let's actually go ahead and just view data types.nasm so that we are able to figure out what to expect for each of these variables, so that now we can inspect them inside GDB, right? So in reality, all I'm trying to do is, we've defined some of these variables and now we want to use GDB to inspect them while the program is loaded and running, right? So the first thing we want to inspect is var1, which is at this address, and we know it's a byte with value 0xAA. So there are multiple ways to do it. You will use the examine x command. If this is unfamiliar, please watch the security tube GNU debugger expert videos, which I just referenced in the slides. I've mentioned how to use stuff there. And one of the ways is to go ahead and use this address directly, which gives us the value 0x0a, which is what is var1. Another alternate way would be to go ahead and feed the address of var1, right? Both ways would work. So we figured out var1. Now var2 basically is a sequence of bytes bb, cc, dd, right? Okay, so what we want is a sequence of 3 bytes which are going to be there at var2, and as we clearly see, it's bb, cc and dd, right? Similarly, now if you want to look at the word at var3, we know this basically would be 2, 3, and if you notice, it's EE00, just as we would expect. And the next one is basically 4 bytes defined together, var4. Now this is where I want to look at how data is being stored, right? And if you remember what we said, that dd would be stored in low memory, cc in the next byte, bb in the next byte, and so on and so forth in higher memory. Let's verify this. So let's figure out the address of var4. So one of the ways you could do that is just to use print. This gives us the address of var4. Now let's print each of these values as hex, starting from this address. So we see dd, and basically this is the next address. Change B to C, this is the next address. C to D, this is the next address, right? If we go back here, what we said was DD would actually be in the lowest address value, which is exactly what we are seeing here. After that, CC would be in the next byte, which is in higher memory, and that is exactly what we see. and then BB would be in the next byte and AA would be in the next higher byte. And you can see this is where 4 plus 1 plus 2 and plus 3, which shows that progressively we are going in higher memory. And this is exactly what little endianness actually is and means. Right? Fantastic. Now, similarly, you can explore other variables. Right? So this is basically var 6 among others, and I leave the others as an exercise to you. There's nothing much over there, but please do this exercise so that you are completely aware about how data is getting stored in memory, how it's defined, and how you can figure out data in various segments and look at how they look like in the program's memory. So that's all for this video. Thank you. Hey guys, so in this exercise, we are going to look at how the stack functions, right? We will primarily look at the push and pop instructions, and I would leave it to you as an exercise to look at push A, push AD, and pop A, pop AD instructions. So let's get right to the program. So I have already written some sample code to illustrate how the push and pop instructions work. In the previous video, we had a look at how the stack itself works with a simple illustration. And now let's jump into the actual code. So as far as push and pop instructions are concerned on IA32, you can push 16-bit or 32-bit values on the stack. Now the values you're pushing can be within a register or can be referenced from memory. So let me give you some example. I have a move instruction here which moves the values 66, 77, 88, 99 into EAX, and then the value 0 into EBX, and the value 0 again into ECX. Right, and after this we are going to go ahead and push and pop instructions. So in this first set I have pushing and popping illustrated of 16-bit values and 32-bit values, right? And in the second case I have pushing and popping using memory, and of course finally we gracefully exit the program. So let's go ahead and run this program and trace through it using GDB. Now how would we go ahead and do this? Well, very simply, first is you need to go ahead and assemble and link it. Done. Let's load this up in GDB with the -q option, or you could skip that if you like. Set disassembly flavor to Intel. Going to break at the start, and let's just go ahead and run the program. Let's disassemble, and you see the disassembly code here. So previous to what we did in the last video, I want to set up certain registers and memory locations which are printed every time we step through this program and the program stops, right? So let me use our friend display again, display EAX, EBX, ECX, and then after this let me actually go ahead and define a hook stop, and within this let me examine the memory, right? Now to examine the memory we need to first figure out where the memory location is, and in this case we are going to reference it with ESP, or the top of the stack, right? So we're going to go ahead and use the examine command, look at 8 consecutive bytes pointed to by ESP. Then we are going to look at 8 consecutive words, and then basically double words. Right, actually let me go ahead and modify this a little bit so that we just see pertinent information. Let me write the hook once again for a second. Sorry about that. So let's override the hook and let me look at 8 bytes first from the beginning of ESP. Now we'll chunk those bytes into basically words of 16 bits, right? To do that, we are going to use 8xh. Sorry, it's going to be 4xh $ESP, and then we want our 32-bit assemblies together. For this, it's going to be 2xw $ESP. After that, we want the disassembly as well. So let's say disassemble $EIP plus 10, and then we can end this. Let's go back in here, and now let's step through the instruction series. This is going to load EAX with this value, which is fine. It's exactly what we see here. This is the memory location which is currently there, pointed to by top of the stack, by the way. The next instruction loads 0 into EBX and ECX, which is fine. Now comes the interesting part, right? We are going to push AX onto the stack. Now AX is basically 8899, and you would actually see that top of the stack is going to reference that as soon as the next instruction is executed. So we've executed the next instruction, and if you notice, 8899 is now on the stack. Due to little endian architecture, right? That's why it's the orientation you see the way it is. Now, interestingly, if you note that because the stack grows from high memory to low memory, as you load more things on the stack, the value of ESP decrements, right? So right now, if you notice, we basically had BF, FF, F3, B0, which definitely is a greater value than BF, FF, F3, AE, right? And by what value? Well, it's basically 2 bytes. Now the next instruction would be to pop the top of the stack into the BX register. Because BX is basically 2 bytes, this value would now get popped from the stack. You would see that ESP, which is this value currently, would be restored back to this value. So let's go ahead, hit that again. And if you notice, ESP again now points to B0. And interestingly, BX contains 8899, which was popped from the stack. Now, let's go ahead and push EAX again. This time, if you notice, we are pushing the whole 32 bits, and the top of the stack now contains 66, 77, 88, 99. And the next instruction will pop this into ECX, which currently contains 0. And when the pop happens, the ESP value automatically changes. There you go. ECX now contains what was there in EAX, and the top of the stack is adjusted as well. Now remember, a push instruction does not change the source in any way, right? It just copies what's there on the source to the top of the stack. And that's why push EAX is not going to change EAX in any way. Now the next thing we are trying to do is to push in a word pointer, which should basically be 2 bytes located in the data segment. Here, let's look at what this is first. We use the examine command. Word would be basically 2 bytes. It should basically be XH. So the value in question is BBAA. Let's run next I once again and see if this is what now is at the top of the stack. And as expected, right, BBAA is now there on the top of the stack. Now let's pop this into ECX, which currently contains this value. And here is something interesting which you're going to do right now, is push directly by referencing a memory again, but this time it's going to be 4 bytes. So let's look at what is there in this word. So this is the value DDCCBBAA, and you would notice that when we run next I, this now gets put on the top of the stack. Now the reason I had you do these other two visualizations as well for the stack values is if you try to read this in a byte format, you would actually see them all being put in the reverse direction, while if you kind of go ahead and read them in the word format, you would get them in the form of a whole word, right? So you can go ahead and add just for a byte, 2 bytes and 4 bytes so that you can see the visualization very, very clearly, right? Fantastic. Now let's pop this value onto EDX, which is basically going to go inside EDX now, which we have not displayed. We could display in just a second. There you go. So if you notice, this value is now inside EDX. And finally, all we are going to do now is exit the program. Right, there you go. Fantastic. So this is how we can use GDB and trace through the stack to understand how values are getting pushed and popped from it, right? If you understand this, then pretty much you understand all of stack arithmetic. Now my recommendation would be to write many more of these instructions and use exactly what I've done right now to follow through what is happening on the stack by following the value of ESP as the instructions are getting executed, as well as monitor the registers which you're using along with those instructions. There are some variations of push and pop which I'll leave to you as an exercise to figure out. That's all for this video. Thank you. Welcome back. In this exercise, we will look at multiply and divide instructions in assembly language. So the multiply instruction and divide, both of them are very interesting. But before we get into the specifics, conceptually, if you think about it, if a register size is, let's say, 8-bit and you multiply two numbers, there are two possibilities. The result of the multiplication would still fit inside 8 bits, or the result of the multiplication may extend beyond 8 bits, right? And this is really what the multiply instruction addresses in its various different forms. So there are 3 variations. One is where you use an 8-bit register or memory location. The other is a 16-bit register or memory location. And the third is 32-bit register or memory location. Now in the first case, when you want to multiply with an 8-bit number, it is implied that the first number for the multiplication is stored in the AL register, and the second number can be a reference to a memory location or another register. And the output or the product is going to be stored in the AX register. Now remind yourself, AX has both A high and A low, and this is where when I talked about the multiplication product being larger than 8 bits, right? Now the important part here is the microprocessor would want to tell you that, hey, the value which I have ended up with in the product is actually larger than 8 bits, right? And the way it indicates that is by setting the overflow and the carry flag to 1 if the upper half of the result is non-zero. What do you mean by upper half? in AX, AH would be non-zero, which is expected if, of course, the product is going to be greater than 8 bits, which is the size of AL. So again, summarizing, AL into an 8-bit number which is in a register or referenced from memory. The output is in the AX register, which can be broken up into AH and AL. In case AH is used, then the overflow and carry bit are set to 1. Now, if you move that from the perspective of 16-bit multiplication, then we use the AX register, which is the implied 1, and the output is stored in a combination of DX and AX register. So this is where the DX register comes in. So the upper half of the result would be in DX and the lower half would be in AX. Now, if the result results in a non-zero DX, then the overflow and carry bit, or the carry flag, sorry, are set. Similarly, when you move on to 32-bit multiplication, we use the EAX register, which is the implied 1, and multiply that with a register or a memory location which is 32 bits in length, and the output is stored in EDX EAX register combination. Now, when you look at this theoretically right now just on the slide, some things might be confusing, right? So let's jump right into the code. Okay. Now, I mentioned that in multiplication, the implied register is the EAX register by default, right? So here is what we are doing. I'm going to show you multiplication 8-bit using registers first. So we first move 0 into EAX to clear it up, and then we move the value 10 hex into AL, and then we move the value 2 again hex into BL. Now when we type in mul BL, what this really means is multiply the content of AL with BL, which is 10 into 2, which is 20 in hex, and the result will be stored inside the AX register, which should have A high and A low. But as you can clearly imagine, because the multiplication is still well within the limit of 8 bits, AH is going to be 0 while AL will be 20, right? However, if you look at the next instruction, then we move the value FF into AL and then multiply with BL, which is 2. FF into 2 would be greater than 8 bits, which would mean now AH and AL both would be occupied. So let's take this very simple example up first and trace through GDB to look at how all of this looks like. And then let's break start, let's run, disassemble, and the very first part of what we talked about is all in here at the very top. Okay, so we want to go ahead and monitor the AL register and the BL register, and of course AX to monitor the output, right? So let's do the following. Let's write a quick GDB hook. And the way we are going to do this is, just a second, with the define hook stop, and the first thing we want to look at is the AX register, low register actually. So AL print below, and then we finally are going to print the AX register in entirety, and of course use disassemble to disassemble $EIP and the next couple of instructions, right? End. Now let's move on to executing the next instruction, and as expected, the next instruction is or the one after that is going to move the value 10 inside AL. So this is AL, this is BL, and this is going to be AX, right? So let's go ahead and run this. And now if you notice, AL is 10, which actually also means that AX would be 10 as well, because A high is 0 at this point. Now we're going to move the values 2 inside BL. Fantastic. So BL now has 2 in it. And if we were to go ahead and print the multiplication output, which is going to be the next step, right? Mul BL. So which means now 2 would be multiplied with 10 to give 20 here as well as 20 here. And this is exactly what we are seeing. Now a variation is, let's load FF into AL, which we did. And now when I multiply by DL, you would need to see interesting things as well. So let's go ahead and print the flags. Right now this is the state. Now after the multiplication, the carry and overflow, both of them would be set. So let me run the next instruction. We run it, and if you notice, it's overflowed beyond AL because EAX now is 1 FE rather than just FE. And now if I look at the flags, you would see that the carry flag and the overflow flag has been set. Fantastic, right? And this is exactly how multiplication works in a very simple way. Now, all I have done in the remaining part is kind of extended this to 16-bit multiplication here. And each of these I basically have two demos, one in which there is no carry or overflow happening, and the second one in which carry or overflow is happening, right? Similarly, I have something in here for 32-bit, and then multiplication using memory locations, which is var 1, 2, and 3, which I have kind of defined down below here, right? So trace through with GDB and try these on your own, because I mean it's exactly the same process. The only thing when you get to 16-bit and 32-bit which you need to remember is that the result of 16-bit multiplication would be in DX and AX, while the result of 32-bit multiplication would be in EDX and EAX, right? And just to illustrate that, I'll just take one example. Let's do the example for the 32-bit multiplication here. I think probably for the one down below here, probably use this one. And let me invoke GDB once again. Now, if you don't run it, but you still want to look at the disassembly, right, you could basically mention the address of start, the star in front, or directly underscore start as well. It's playing with you. It's basically giving the address and then dereferencing it once again. So you could use either ones if you'd like. So let's kind of go down below. And this is the multiplication we are interested in, right? Which is at plus 59 from the beginning of start. So one of the other ways you can set up a breakpoint is exactly what I showed you right now. Plus 59, here is doing it, and there you go, right? And this is the place where we have set up the breakpoint. Let's run the program so that we hit just our breakpoint. Now let's do a quick disassemble. Let's do a disassemble from $EIP, just the next 10. Okay, EIP is still kind of up there. So let's continue so that we hit the second breakpoint, which is what we are really interested in. And there you go, right? This is the multiplication happening in here. Now, let me actually set up a little display for us for $EAX. Actually, let me set up EDX up on top. And then I'm going to set up EAX. And then I'm going to set up EBX. And then I'm going to set up display of the flags. Right? And now let's step through the program and let's also set up debug stop with disassemble for $EIP plus 15. Now let me do a next I. Not sure why the disassemble did not. Yep. Yeah, it was hook stop. It was not debug stop. Thinking something else while doing, and this is what happens. Okay, so I think at this point, if I just do a disassemble real quick, where we are is now EBX is going to get loaded as well, right? Go up in here, next I. So EAX is currently loaded with this value, EBX is currently loaded with this value, and EDX right now is 0, right? Now, as far as 32-bit multiplication goes, the output is going to be in EDX, which is the upper 32 bits, and EAX, which will have the lower 32 bits. So if I run the next command, there you go. If you notice, EDX and EAX together contain the output of the multiplication. Now, this is something you can verify if you like as well. So I can basically launch the calculator, and this is the first number, 11, 22, 33, 44, 11, 22, 33, 44, multiply that with 55, 66, 77, 88, and if you look at the output, the first 32 bits or the higher order 32 bits is 5B 73, 6A 60, which is exactly 6A6, sorry, which is exactly what we have here. And then after that, you have the remaining bits down below, which is exactly what you have inside EAX. Now, the irony is that we are using a calculator running on the same machine to judge if the multiplication of a program on the same machine is correct, which means if they were wrong, both would be wrong. But hey, congratulations Intel, the multiplication works, right? Your mul instruction works. Okay, so and if you notice, the carry flag and the overflow flag, both of them have been set because the EDX register is being used, right? Fantastic. Now, what I'm going to do is let me discuss the division instruction. Now, division, just like multiplication, has a very interesting format. So when you want to do 8-bit division, you divide AX by an 8-bit number which can be in a register or referenced via memory. Then the quotient would be in the AL register while the remainder would be in the AH register. When we do that for 16-bit, and we use a combination of DX and AX to denote the whole number, the quotient is in AX, the remainder is in DX. And when you do that for 32-bit with EDX, EAX, then the quotient is in EAX while the remainder is in EDX. Now, the best way, as you always know, to illustrate this is with the example. In the same file, if you kind of scroll down below, I have, I think, 2 examples of division. You can put in your own later on and try more. So what I'm doing is, in the first example, I actually have dx set to 0. So I'm going to do 16-bit division, where dx, or the higher order 16 bits, is 0, ax is 7788, and then I'm going to divide it with the contents of the cx register, which basically would be containing 2, and then call divide. Now, based on what we've seen in here, the result of the division would result in the quotient in ax and the remainder in dx. So let's go back here. I think this program is still useful in the sense, let's do a quick disassembly and let's go directly to the division where we were interested, right? So the division is here. So let's just set the breakpoint here for star. And I'm showing you multiple ways to set the breakpoint, guys. You could set it up in any way you're comfortable with. Let's continue. We've basically hit the breakpoint, and now let me do the next I, so that we're going to move 0 inside dx. I think we are not displaying okay, we have dx, great, fantastic. So if you notice now, dx is actually 0. I'm going to move ax 7788 inside ax, which is what we have in there right now. Going to move 2 inside cx. Okay, we can't see that, but do a quick print on it and verify the same. There you go. And now I'm going to divide with cx, right? So let's do a next I again. Fantastic. And if you remember, what I told you is that the result of the division, 16-bit, the quotient would be in the AX register while the remainder in DX. So the quotient in AX, which is the lower 16 bits, which evaluates to 3B/C4, and the remainder would be in dx, which evaluates to 0. And if you'd like, you could verify the same thing as well. So let's put in the values again. We basically had 7788 and we divided it by 2. Note, everything is hex, guys, okay? Don't forget that. And if you notice, the response is 3B/C4, which is exactly what is there in AX, right? And you could print all of them separately as well to order to avoid confusion. There you go. And the remainder is 0, right? Fantastic. Now, in the next division, what I've done is I've just used one more, which is instead of 77 plus 7788, I've used 7789. And what this really means is now we would have a remainder 1 in dx, right? Which would mean ax would still contain this value after the division. It's just that dx would contain 1. Let's go through this. Next I, and I'm going to allow the divide to run before we inspect the registers. Next I. And now if I go back to printing ax, I would have the same value 3B/C4. However, when I print dx, I would have the remainder 1 in it as expected, right? Fantastic. So this is how multiplication and division works. I would advise you to create more examples for yourself and try it out. It's not really complicated, just you need to get that idea in mind that multiplication and division requires 2 registers, EAX and EDX together to get the job done, right? And you need to closely watch the carry and overflow flags for multiplication to figure out if there is an overflow. Now, apart from just the mul and div, which is for unsigned arithmetic, you also have signed arithmetic, where the sign, if it is positive or negative, is taken into account using imul and idiv, which I leave to you as an exercise to try out, right? If you understand what I've taught here, pretty much imul and idiv just has a couple of other interesting things with respect to sign. So that's all for this video. Thank you. Hello all. In this video, we will look at logical instructions in assembly. Now, logical instructions are similar to what you've seen in other programming languages like C, Python, etc. The very base instructions, of course, would have to be AND, OR, XOR, and NOT. Now, the destination operand for AND can be a register or a memory location, while the source can be a register, memory, or an immediate value, right? 8, 16, and 32 bits allowed. However, you cannot do an AND between two memory locations. Now, the relationship is that this is going to be a bitwise AND operation, and the bitwise AND operation, the output of that is stored in the destination, which is the first argument. So just a quick refresher, 1 and 1 is going to be 1, 1 and 0 is going to be 0, right? Similarly, you have OR, where basically, 1 or 1 is basically 1, 1 or 0 is basically again 1, and 0 or 0 is 0. XOR is nothing but if you have two numbers A and B, then you basically have A B complement plus B A complement. And NOT is just the inverse of that value, right? The key thing here is all these operations are bitwise operations. So let me take you directly to the code to give you a sense of how this feels. So I have illustrated the usage of AND, OR, XOR, and NOT as part of this exercise file, which is logical.nasm. Let me show you how it looks like. So the first instruction is moving the value 10 into AL, and I'm going to just say 10, 12, and all of that. Remember, it's hex the way it has been represented. So move the value 10 inside AL, and then do an AND operation of AL with the value 1, right? In the second part, I am using a memory location as well and an immediate value. Now the memory location var1, var2, var3 are mentioned here at the bottom. And the first instruction is to do an AND operation between the value AA and var1 and store the result in the location by var1. And here in this case, the result of the AND operation would be stored inside AL. In the second AND operation, I'm basically going ahead and doing an AND between var2 and the value 1122. Of course, the destination for storing the result is basically var2, right? Similarly, I have illustrations of OR, XOR, NOT. So let's actually go ahead and assemble and link the code and run it with GDB and trace through how this looks like. Okay, now let's disassemble. So in this case, what we are doing is we really want to track AL. We want to track the EX register in totality, and we want to track var1, var2, and var3 for this entire exercise. Right? Fantastic. So let me go ahead and type in display $AL EAX, and then I'm going to write a hook stop inside which I would like to examine memory, and var1, if you remember, was just 1 byte, var2 2 bytes, and var3 4 bytes. So in order to examine just 1 byte in hex, this is how I would want to do it. var1, var2, see, var3, and then I would like to disassemble from $EIP and a couple of instructions after that. And here is my hook, right? So let me do a quick next I. So this is var1, it's okay. This is var2, var3. This is the value of EAX right now and AL here, right? So the first instruction, if you're going to recall, was moving the value 10 inside AL, which is exactly what has happened here. The next instruction is going to be an AND between AL and the value 1. Now if you're going to write them out bitwise, what you would actually see is that really there is no overlap between the two bits, which is the AND is going to go ahead and result in a 0, right? Now if you look at the next statement, we want to do an AND with basically var1 and the value AA. Now AA is exactly the value of var1, which means all the bit positions would kind of align up, right? So the places where there are ones in the whole bit mask for AA, exactly the same positions would have ones in the case of var1 because the values are the same. And hence this AND operation would basically yield exactly the same result, which is AA. And this is the reason why var1 remains unchanged even though it was actually overwritten. Now in the second case, we're going to now do a bit mask ANDing with var2, which is BBCC, with the value 1122. Of course, this would have some effect. The exact effect of what this is something you would need to figure out by writing all the bits individually and doing the AND yourself, right? Now let's move on to OR operation. Now in the case of OR, we'll take the exact same example. So we're going to move the value 10 inside AL. We did that, and now we are going to OR with the value 1. Now if you write this in a bit mask format, you would see that the result would be an 11, right? Because 1 or 0 is 1. Unlike in the case of AND, where 1 and 0 was actually 0, and 0 and 0 was 0. Okay. Similarly, now if we kind of go ahead and do an OR with var1, so AA or AA basically goes ahead and again remains just AA, nothing really changes, right? When you OR and value with itself, nothing changes. Now in this part, we're going to look at another interesting example. So let's just go ahead and move on to more statements, which is the XOR operation. Now XOR is something which is exceptionally interesting, and this is something we are going to use time and again when we move on to shell coding. Now the interesting property of XOR is that if there are three numbers A, B and C such that A XOR B is C, right, then C XOR B is going to give back A and C XOR A is going to give back B. And this property is what we exploit while writing a XOR encoder. Now what does this really mean? So let me give you an example. We are going to do a XOR of the value 11, 22, 33, 44 with var3, which is again 11, 22, 33, 44. right, which is exactly the same value. And what you would find is XORing two exactly same values is just going to yield 0. So the result of this operation would be to store the value 0 inside var3. And this is exactly what happened. Now the XOR of 0 with any number is that number. So which means if we XOR 1, 1, 2, 2, 3, 3, 4, 4 with 0, we get back the same number as a result, which is 1, 1, 2, 2, 3, 3, 4, 4. And that will exactly what will get stored back here when we run this instruction. There you go. Fantastic, right? Now keep this property of XOR in mind, because A XOR B equals C, which would mean C XOR B is A or C XOR A is B, is something we will use in shellcoding. Now moving along, let's move the value all F's inside EAX. Now not EAX is just flipping all the bits to the other state. So a bit which is 1 would be 0, a bit which is 0 would be 1. Now all F's would mean all bits are 1, which would mean not EAX would result in all zeros. That's exactly what happened here. And now not EAX again, which is not on all zeros, would flip back to all FF. Here you go, right? So this is all for the logical instructions. They are a very easy instruction set to deal with, but this is something we'll use time and again when we look at shellcoding. Now apart from these, you also have other instructions such as shift arithmetic write, SAR, SHR, shift logical write, ROR and ROL, etc., which is rotating of instructions. I'll leave it as an exercise to you to look into more of them. The AND, OR, XOR, NOT probably are the more fundamental ones which you will encounter when we do shellcoding, right? So that's all for this video. Thank you. Hello all. Welcome to this video in which we will discuss about control instructions in assembly language. Now, control instructions essentially control the flow of the program, and the direction or branch in which the program should go in is typically based on different events or calculations, such as a zero operation happening, etc., which may happen, and the programmer may decide to do something else based on that event. Now in assembly language, control instructions depend a lot on the flags to determine what to do. Now as far as branching out is concerned, there are two options one has. One is unconditional and the other is conditional. Let's look at both of these in this video. Now unconditional branching is actually accomplished using the jump instruction, and it is comparable to the goto statement in C programming if you've done it before. Now the unconditional jump has two types. One is called the near jump and the other the far jump. The near jump is when you want to jump to an instruction which is there in the current code segment, which is the segment doesn't need to change. While the far jump is when you jump to a totally different segment. The near jump has a subtype called the short jump, which is basically jumping to an instruction minus 128 to plus 127 from your current position. Conditional jumps are more interesting, right? Because this is really where decision making based on different events happening in your code happens. So JXX, and the reason I mention XX is there are tons and tons of conditionals available. So JEZ is jump on 0, JNZ is jump on not 0, JA jump on above, blah blah blah, and all of these use flags to decide whether to jump or not. So as an example, JZ will jump if the 0 flag is set, right? And let me take you directly to the Intel manual, and this is volume 2 of the Intel manual, and if you search for the JCC, which is jump if condition is met, you would see a ton of them. You can see jump if basically above, jump if above or equal to, jump if below, and it's really a ton of them out there, and you need to familiarize with many of them. And almost all of these, as you can see on the right hand side, depends entirely on the different state of the flags. So please refer to volume 2 of the manual in order to figure out an exhaustive listing of all the jumps allowed, right? So as an example, if you notice here, this one basically is jump if not 0, and interestingly, you basically have a ton, really a ton of conditional jumps, right? Now, one of the things with conditional jumps is they cannot be used with a far jump, and the Intel manuals gives you an interesting solution. It says whenever you need to do a far jump based on a conditional, you could use this format, which is JNZ label 1, which is if this is not 0, go to label 1 and execute. If not, the next statement is actually an unconditional jump to a far label. So in reality, if you think about it, hitting this would actually mean a conditional far jump, right? Now, to be honest, the Intel manual is the best reference. There is no point in me really just cut, copying, pasting from the manual here. You should read the appropriate page here. So I think page 474 onwards. It's kind of 3 pages of all the conditional jumps which are there, right? Fantastic. Now let me actually jump in and show you the usage of both unconditional as well as conditional jumps. Now what I've done is I've cannibalized a little of the Hello World program which we had. And let me show you how this works. Let's trace through from start because that is the entry point. So at the beginning we have an instruction which says jump to label begin, which is here. Now if you notice in between I have a little stretch of code which basically is never going to execute, referenced by never execute. The reason is the jump instruction is unconditional, which means if you hit a jump, it is going to happen. There is no way that that jump instruction would be ignored, right? And that's the reason why this piece of code in here is never going to be executed. Okay, so we hit jump begin and we are here. Now what I want to do is I want to print hello world 5 times using conditional jumps. Now the lower part here, which is calling sys_exit, remains the same, and all I want is this part here, which is the core code of printing hello world, should be repeated 5 times using conditional jumps. Now there are multiple ways to do this. I want to use the 0 flag. So here is what I'm doing. I set the value of EAX to 5, and logically what I want to do is decrement this value of EAX every time I print hello world on the screen, and finally once it is done running 5 times I want to stop printing hello world, move on and gracefully exit the program. Now there are 2 key concepts here which you need to consider. The first is we are using the EAX register to store the number 5, and we seem to be using the same register to invoke the syscall because the syscall number needs to be there in the EAX register. What this means is that we essentially end up overwriting our counter. So how do we maintain state in the counter? Now there are multiple ways of doing this. A very simple way is to use the stack. So what we want to do is, before we invoke the syscall, we store the state of the program, which could be multiple registers, but in our case just the EAX register on the stack by calling a push EAX. Now, after we are done executing the syscall, we would like to recover that value of EAX so that we can decrement it and check if we've finished running the print hello world part 5 times. So we pop the value of EAX back into the register. We decrement it by 1, which is dec EAX. Now, till the time EAX does not become 0, the 0 flag would not be set. And in which case JNZ or jump on not 0 would be the jump instruction we would execute, right? And JNZ basically says jump on not 0 to print HW, which is print hello world label, which basically brings us back in here, which is this instruction to execute. Now, the moment EAX decrements to 0, the 0 flag is set. JNZ no longer would be executed because now the 0 flag is set, and we move on to the next instruction, which proceeds to gracefully call sys_exit and exit the program, right? Fantastic. So let me go ahead, run the program, and you can clearly see we are printing hello world 5 times. Now let me go ahead and use GDB to trace through the program so that we know exactly how the state of the program has changed over time. Right? So the first thing we encounter is really the jump instruction. Here is what we are going to do. What we would like to monitor is the EAX register. So I'm going to say define, let me use a display for EAX. And let me use a hook stop so that the disassembly happens. And let me do a next tag. There we go. So the unconditional jump has happened, and now we are at begin, which is going to move the value 5 into EAX. Okay, 5 has been moved. Now we are going to push the value of EAX on the stack. So let me examine the stack as well. Let me examine just the first word, the first double word, which is 4 bytes stored on the stack. Okay. Now once we execute this instruction, EAX would be stored on top of the stack. The value of EAX currently is 5, and we'd see that that is what goes on the top of the stack. So let me do a next I. And now when I look at the stack, you would notice that the value 5 is being stored on the top of the stack. Fantastic. Now, the next instruction or the next series of instructions is something which is going to go ahead and call syscall. So let me just quickly, step through it. So syscall would be called now. And if you notice, the first hello world was printed. And now we pop the value back into EAX, because if you notice, EAX has the value D in it. After the pop, it has the value 5 again. Then we decrement EAX by 1, which makes it 4. But at this point, if we look at the flags, you would see that the 0 flag is not set. Right? So let's go ahead and continue running the program for a couple of more times till the time EAX doesn't become 0. Okay. Now, the next instruction is going to be DEC which would make this 0, and you would actually see that the flags would change as well. There you go. EAX is now 0, and if you notice, the 0 flag is set, which means basically this would actually go to the other one, and we move on, and it goes ahead and finishes off the remaining part. Fantastic. Now, you may notice, interestingly, that if you do a quick disassemble, the the J and Z which I had is being replaced by a J and E. And I leave this as an exercise to figure out why and how, and why NASM did this, right? Anyway, coming back, the exercise I want you to do is to investigate on another instruction set which kind of helps us with doing loops, which is exactly what we did right now with J and Z, J and E, which is loop Z, and loop NZ. Right? Try this out and see if you can do the exact same program which we have here, which is printing hello world 5 times using the loop instruction. That's all for this video. Thank you. Okay, so welcome back. Now in this exercise, we will look at how the loop instruction works. Now let me directly take you to the code, and the file we are going to be using is called loop.nasm. And I've just done one small change, which is replace the J and Z with a loop instruction. However, a couple of other interesting things. Now, the loop instruction works in the following way. It basically is dependent on the ECX register, which is your counter register. So you can load a value into ECX, and then you can call the loop instruction with a label. Now, till the time the value of ECX is not 0, the loop instruction would continue to call the label and keep looping. Note that the loop instruction automatically decrements ECX as well, and that's the reason why we do not require a DEC ECX like we did in the previous case, right, where we use DEC EAX. So basically the only change is I'm moving the value 5 into the ECX register. I push it because I use the ECX register for the syscall. Then I pop it back from the stack, and then I call loop, which decrements the ECX register, checks if the value is non-zero. If it is non-zero, calls the instruction at the label print HW, which is back again here. If it is 0, it basically moves on to the next instruction, right? The variants of loop, which is loop E and loop NE, both of these additionally use the 0 flag, which you can have a look at and see how those variations work, right? So it's pretty much simple. Let's go ahead and generate the binary, and if you run loop, you have your hello world once again 5 times again, right? Fantastic, right? So looping, when you especially want to loop for a count number of times, is best done with the loop instruction. JZ, JNZ, and all of these are when, you know, unpredictable things are there, which is you do not know a priori probably the count number of times you would have to do the loop and things like that. I think JZ, JNZ come in handy there. And I think just try it out. I mean, try out loop E and loop NE as well and see how you can fit those variations, right? That's all for this video. Thank you. Welcome back. In this video, we will look at procedures in assembly language. So a procedure in a layman's language is a set of instructions grouped together. So as an example, in hello world, all those instruction sets which we had which is setting up the registers with the right value for the syscall number, the pointer to the message you want to print in hello world, the length, etc., all belong together. So you could think about a simple procedure which could just print hello world. Now in NASM, procedures are just defined by labels. There is no specific keyword for procedures in NASM. It's important to note that other assemblers do have keywords such as proc available to define procedures. Now in reality, the reason why it doesn't matter is in assembly language, there is really no procedure per se. It is just another flat listing of code which you want to call in a specific way, right? Now calling a procedure happens using the call instruction followed by the procedure name. Now how would a procedure look like? So you first define a procedure name, which is nothing but a label, and then after that you write out all the code you would want executed when the procedure would be called. And once you're done, we end procedures with the ret instruction or return instruction, which tells the CPU that, hey, we are done executing the procedure and to go back to the next instruction line from where this procedure was called. Now let me try and show you a piece of code to make you understand what I mean here. Now this is again the same hello world program, but I've done one interesting modification, is that if you note, this entire piece of code which is responsible right from move EAX4 to int 80, I've kind of moved it, and I've moved it into a procedure using a label by the name of hello world proc or hello world procedure, right? And after the printing is done, I call the return instruction. Now there are various places you can actually go ahead and put your procedure in. There is no hard and fast rule, but it's a good idea to just stick to one specific method of doing it. For example, I like to define my procedures higher up in the text segment before I actually have my underscore start or entry point defined, right? This also ensures that accidentally procedures are not executed just probably by a procedural following of the code. Okay, so what have I done here? I have underscore start, which moves the value 10 inside ECX in hex, of course, and then I have a print hello world label, and all this does is it uses ECX as a counter like we've seen in a previous video, loops over print hello world, and just calls hello world proc for every single iteration. Now there are two things which you need to keep in mind about procedures. Now we may call procedure here, and as soon as the call is hit, the CPU moves to executing this, finishes, comes to int x80. Now when the return instruction is hit, how would the CPU know that the next instruction to execute is actually pop ECX, right? There's no way. And this is where what the assembly language instruction set does is that as soon as a call command is hit, the address of the next instruction, which in this case is pop ECX, is actually pushed on the stack, right? And the ret instruction pops that value from the stack back into the EIP register so that the CPU knows that this is the next instruction to be executed after the procedure returns, right? This is the only key concept which you need to keep in mind. Now let's go ahead, assemble, link this demo, follow through GDB to see if all of that is true. Okay, assembling and linking done. It runs as desired. I think 16 times. Would go ahead and put out hello world. Now let's load this up in GDB, have some more fun with it. So here we go, our regular stuff, break underscore start, Let's run the program. We've hit the breakpoint, do a disassemble. Right now we're just moving the value 10 inside ECX, so it's really nothing we need to worry about. You can look at the different functions, and if you notice now, basically all the labels you have are listed including hello world proc. So you could actually do a disassemble this address, and this is our procedure code. This prints hello world onto the screen, and here is the ret command, right? And let's now step to the program. And disassemble. So the next command is just to push ECX on the stack, which is I think something we've already seen. So let me just set up a define hook stop disassemble, and right, let me do a next I again. Okay, so now we are just about to call the procedure, and I said as soon as the call instruction shifts control to the procedure, which would be here, the next instruction set's address, which is basically pop ECX, would actually be pushed onto the stack. So let's also go ahead and look at what is there on the top of the stack right now. Okay, so it's basically a value which we just pushed, which was ECX, right? Now, as soon as I run the next instruction, and now if I look at the stack, you would actually notice that the next value pushed in 080480882 was nothing but the address of the instruction pop ECX, which is the next instruction to be executed once we return from the procedure. Now all control has gone to the procedure hello world proc, right? So let's go ahead, do a quick next I. Hello world got printed, fantastic. Now the other thing is, let's again go back to observing our stack. And as soon as the ret instruction is hit, basically this is equivalent to a pop $EIP, which would go ahead and pop this value inside the EIP register, and the next instruction to be executed would now basically point to pop ECX, which is this line here. So let's see if that is true. Let's hit a next I, and if you notice, now we are at pop ECX, and right now the top of the stack would only contain the value 10, right? So this is a very, very key point which you need to remember, that EIP is pushed on the stack when a call happens, and EIP is popped back from the stack when a return happens, right? This is really the essence of procedures, and I think the rest of it is pretty clear to you. We just go around in a loop, and basically the program exits. Let's go back. Now there are multiple ways to send arguments to procedures. One of them is to pass them via registers, the other is to pass them on the stack, and the third is via data structures in memory, while those references to those places in memory can be passed via registers or stack, right? When we look at how to use libc and all of that in assembly, we'll talk about passing via stack. Passing via registers, as you can imagine, is clearly trivial, right? Now the other important aspect is, inside a procedure, a ton of things may be happening, right? Registers may be changed, flags may be changed, the whole state of the program may change. Now this could be entirely desirable, while at the same time there would be situations where you would want to preserve the state of current registers, flags when you enter a procedure so that you can restore them after you return from the procedure. So the simplest example is basically what we have in our own code, which is we preserve the value of ECX before we call our procedure, right? Because our procedure seems to be using ECX as well. So we preserve ECX and then we restore ECX after the procedure returns. Now, there are different instruction sets we've already looked at as to how this can be done. Apart from the flags as well as the registers, you could also be saving frame pointers, which is basically EBP, using the enter and leave instruction sets. Now, I would want you to investigate into enter, leave along with the ret and look at this next exercise, which is you need to write a program which now saves all the registers and flags before calling a procedure, and it should also save and restore the frame pointer, right? So have a look at this. This is the exercise we will solve in the next video. That's all for this video. Thank you. Hello guys. In this video, we will look at working with strings in assembly language. Now, by this time, I would start assuming that you can look up the Intel manual and figure out what each of these instructions does on your own. If you haven't, it's probably a good time that you started doing this research, simply because, as I mentioned, there are literally hundreds of instructions and it would be impossible to cover each and every one of them. But at times, when you're writing shellcode, reversing, or writing exploits, you may come across new instructions which you haven't seen before. And the only way to demystify all of that is to consult the Intel manuals and look at what they do. Anyway, so string instructions, well, the most common ones are moves, compares, scas, and loads. Now, moves is basically allowing us to copy one string to the other. Compares is basically comparison for string. And the remaining two are for subtracting and loading. Now, I leave the remaining two to you as an exercise. As far as moves and compares are concerned, the assumption is that the source string is referenced by ESI while the destination string is referenced by EDI. Now, let me go into actual source code to illustrate how they work. Now, all I'm doing is a very simple copying a string from a source to a destination. So here is my program, and this has code both for moves as well as compares. So it's going to be a bit long, but I'll just talk about the moves one first, right? So in my data segment, I have defined a bunch of variables, if you'd like to call them. First is source, which is hello world, followed by a new line. Then I have comparison, which is just hello. Then I have result 1, which is strings are equal, and result 2, which says strings are unequal. And finally, in the BSS segment, I have initialized 100 bytes inside the BSS segment. Now let's go up here. Now, moves itself has three variations. One is moves B, the other is moves W, and the third is moves D, right? The B1 is to move byte by byte. The W1 is to move word by word, and the D1 is to go ahead and move 4 bytes at a time. We will look at moves B in this example. You can try out the others on your own. So, the first thing, if you remember, would be to go ahead and figure out the length of the string, which is already defined down below. So what I'm going to do is, I'm going to go ahead and have ESI point to the source string, which basically is the hello world string. And I'm going to have EDI point to the destination, which right now is nothing but 100 bytes which have just been reserved, all 0 values. And then I really want to copy the string pointed to by ESI, which is source, which is hello world, into EDI, which is destination, right? Now, the way to do this is we're going to move byte by byte, and as one can clearly imagine, there has to be a way by which we can run this in some sort of a loop. And this is where the rep series of instruction comes in. This is similar to the loop instruction. And what rep does is it's going to repeat the instruction after that till the time the ECX register does not become 0. There are variations of rep which are also available, which I'd request you to have a look at. So, the other thing apart from this is the direction in which the copying is happening. Now, as you can imagine, that source and destination are nothing but two memory addresses. So the question arises, after each byte copy, should we advance the memory address, or should we go ahead and go backwards in memory, which is subtract from the existing address? This is dictated by the direction flag in the eFlags register. Now, if you go ahead and set the direction flag, then the copying would basically happen in the higher memory to lesser memory direction, while if you set it to 0, the copying would happen from low memory to high memory direction. So what I'm going to do is I'm going to go ahead and first figure out the number of iterations we need, which is nothing but the length of the string. Then I'm going to load the address of the store string into ESI, load the address of the destination string into EDI. Then I'm going to go ahead and clear the direction flag, which I want to copy, from low memory to high memory. And after that, I'm just going to repeat MOVSB, which is moving one byte from source to destination, which is nothing but the copy is happening at a time, and this repetition will happen source len number of times. Now, once this instruction is completed, if basically the copying has happened successfully, then now if we just print destination, it should basically print exactly the same string as source, which should be hello world followed by a new line, right? So let's have a look at this. Let me basically load this up in GDB. Let's break, make disassemble. Now this is really the instruction set which we are interested in, but let's also do something by which we can monitor the copying as it is happening, right? So define hook stop, disassemble, and then I would want to print the destination basically in a character format byte by byte. Can end this here. Now let me run the next instruction. Now, if you notice, destination at this point is nothing but all zeros as expected because it is in the BSS segment. Now, we are going to be loading the source strings address into ESI. Done. Now we are going to load the destination strings address into ESI, and if you notice, this is nothing but the address space which you are watching right now. Then I'm going to clear the direction flag, and now the copying is about to start. And what you would notice is basically first you would have H getting copied, then you would have E getting copied and all of that, right? So let's watch that step by step. Okay, so now if you notice, the first time we ran it, H got copied. Now we would expect E to be copied in the next available space. There you go, E. And similarly, you're going to have LLO, the whole hello world kind of going by. And we have the whole of hello world available here. right? Fantastic. Now after this is basically going to be the printing, which we can just continue and see that the printing happens. So here it is, hello world was printed as is, right? Fantastic. Don't worry about the strings or an equal part. I'll come to that in just a bit. Awesome. So this is how you can use movesb along with rep to copy a string from a source memory address to a destination memory address. Now the second thing we would like to look at is comparing two different strings to check if those strings are equal or not. So this can be done using compare sb, which also has the variation compare sw and compare sd, depending on at using what chunks of memory you want to do the whole comparison. So this works exactly the way the previous one works. We load up the length of the string of source, we load up source, we load up the comparison string, which you if you scroll down you would actually see it's just hello, which would mean definitely that this comparison would fail. And then we use rep e. Now this would also go ahead and check whether each of them in the comparison are equal or not, right? So read up the documentation. Basically, if both the strings are equal, then after rep e compare sv is finished, the zero flag would be set. If at any point they're unequal, then basically the zero flag would not be set. So what we do is after rep e compare sb has been run, we actually use a jump on 0, which is if both of them are equal, go to set equal. And in set equal, all I do is I load up result 1 and its length into ECX and EDX so that I can eventually print it on the screen. So if you notice, result 1 says strings are equal. Now in case that the zero flag was not set, which is the strings were unequal, then this gets executed, which is we move result 2 and its length into ECX and EDX so that that gets printed. And after that we do an unconditional jump to print, which just goes ahead and prints it. And result 2 specifically says the strings are unequal, right? Fantastic. So now if I go ahead and run this, as you would imagine, we actually get the strings are unequal. And you could use GDB and set a breakpoint in the appropriate place you're interested in tapping in, which would be we are interested in here. So let's go ahead and have a breakpoint in here. Let's continue. So breakpoint 2 is hit, which is just after the comparison has happened. And at this point, if we print the E flags, you would actually see that the zero flag has not been set, right? Now, instead of using the comparison string, if I go ahead and use the destination string, right? Because up here, the destination string has been overwritten with the source string, so basically both of them are equal. Let's run this first, and you would see it says the strings are equal. Now you could use GDB to load that up. Run the program, set up a breakpoint exactly in the same place, which is just after the comparison rep z is done. Paste, continue, and now if I do a print E flags, oops, you would actually see that the zero flag is set. Now you're noticing that we have rep z here, while we actually entered rep e here, right? So why is this? And this was similar to questions I've asked you previously. I'll give you a little hint. Look at the opcode of both of these, right? See if the opcode is same or not. That will give you the answer, right? So basically, this is how you can go ahead and do string operations in assembly. You can play around with many of these operations, write your own little programs, and most of these commands are used quite a number of times, which is the whole kind of repx along with the compx or the movx to do a bunch of things. And later on, if you look at things like disassembly and all of that, you would see that whenever you locate such a rep structure along with a move structure, basically that copying is happening, and it'll all make more sense to you then, right? Fantastic. So that's all for this video. Thank you. Hello all, welcome to part 11, and in this video we will talk about how to use libc functions in our assembly language programs. Now you're probably asking yourself, weren't syscalls good enough for just about everything? Well, the answer is yes, but if you start using those low-level syscalls, and if you want to create a slightly complicated program, you would just end up using too many of them, a lot more code to write, and definitely this is not something which is desirable, because assembly language is very, very difficult to debug if you compare it with other high-level languages. So what we really want is to be able to leverage the standard C library on Linux, which is libc, which has tons of useful information. And this video will focus on calling libc functions from assembly. Now, the only things you need to remember when you invoke libc library calls is the following. A, all the library calls which you want to invoke in your program need to be defined using the keyword extern right at the top. Second, whenever you call a libc function, the arguments to that function need to be put on the stack, and they need to be put in reverse order. What do I mean by that? If you call a libc function which takes in 4 arguments a, b, c, and d, then you need to put them on the stack in the order d, c, b, and a, right? You can put them using a push instruction or any other instruction. Now, here is the other important thing. To maintain a proper state for ESP, ensure that after your libc function call returns, you adjust the stack accordingly. Finally, we would want to compile the program now with GCC and not with LD, because it's much easier to do with GCC. Now GCC expects a main entry point to be there instead of underscore start or any other random name. So we'll stick to main. Now, however, you note that GCC does have options with which you could give in any other starting point, but we'll stick with main. Having said that, let me take you to the code now. And what I have done is I've recreated the hello world program written using syscalls, now using libc function calls. Now the two function calls I'm going to go ahead and use are printf and exit. So what I told you was the arguments to the libc function calls need to be there on the stack. Now, how do you find that out? Very simply, let's open up a new tab and let me do a man 3 printf, and this gives me the programmer manual page for printf. Now the easiest way to invoke printf is just to feed it the pointer to the string which you want to print. So I have already defined message in here, and of course you would want message to be null terminated, and what I'm doing is I'm pushing the address of message on the stack, and then I'm just issuing a call to printf. Then after printf returns, I adjust the stack size by 4. This is just going to ensure that the stack is back to where it was before. After that, I'm going to move the value A into EAX and then call exit. Now exit would just exit the program, so it doesn't make any sense to do any ESP pointer arithmetic after that, right? So let's go ahead and link and assemble and link, sorry. And what I've done is I've changed compile.sh for this program a little bit here. Instead of LD, I'm using GCC. Also, one of the things which I forgot to mention, that now the entry point is main. Right, so let's run compile.sh, libc. There you go. Let's run libc. And if you notice, the hello world gets printed on the screen. Now let's load this up in GDB to look at how the disassembled code looks like. We need to break on main right now. Let's run the program and let's disassemble. There you go. And here is what we're going to do. Let's go ahead and track the stack as well. So let's just track the top of the stack. There we are. And go to the next instruction. Now if you look at the top of the stack, we basically have the pointer to the message we want to print, which we can verify. With this, sorry. There you go. So we have hello world on there. So let's now move on to the next instruction while still keeping an eye on the top of the stack. So let's just do a step I. And if I do disassemble, this would go ahead and continue into printf, which is something we don't really care about. So let's kind of go ahead and create a breakpoint here for the next instruction after printf finishes execution. So printf has printed it. And now if I still continue to look at the top of the stack, it would still exactly be the same value as before, right? And this is where we do our little pointer arithmetic. And if I kind of go back here, we want to reset the stack back to this value. And if you notice, the stack has now been restored to where it was previously pointing to. And then after that, you just go ahead and continue the program and exit, right? So this is a very, very simple example. But frankly, this illustrates pretty much any libc function which you can use in your assembly program. All you need to ensure is the arguments go properly inside the stack, and then you make the appropriate call, and then you eventually, after the call, you adjust the value of ESP accordingly, right? Fantastic. So that's pretty much what I had in mind for this video. Try this out yourself and play with different libc calls. Thank you very much. Hello all, welcome to module 2, Introduction to Shellcoding. So finally we are there, and in this video we will look at shellcoding basics. Now, if I were to define shellcode in a very easy to understand way, it's basically machine code with a special or specific purpose. Examples could be spawning a local bin.sh shell, binding to a port and then spawning a shell when someone connects to that port from the outside world, creating a new account on the machine, and tons of other such things. Now, the most important thing about shell code is because it's in the machine code format, it can be executed directly by the CPU. No further assembling, linking, or compilation of any kind is really required, which means it can be consumed in its current form by a CPU and executed. Now, how is shellcode delivered? Broadly, there are two ways. One is as part of an exploit. You've heard about a lot of payloads when you use metasploit, such as reverse TCP payload, add account payload, creating a shell payload, etc. These are examples of shell coding being used for payload creation. And in this case, the size of the payload is very important. And typically, smaller the size of the shellcode, the better. One of the other things of importance in here is something called bad characters. Now, bad characters really are those characters which, if they are part of the shellcode, may prevent running the exploit entirely, which is your exploit may fail simply because of that character being there. The most common one is the null character or 0x00, and typically while shell coding, this is one character which we will almost always avoid. There are other bad characters possible as well, and it depends entirely on the program you're exploiting and the specific exploitation conditions which you need to analyze. Later on, I'll give you a link for a couple of free videos I had created for exploit research where some of this is explained more. The other way to deliver shellcode is to basically add it into an executable. This could be then running the shellcode as a separate thread or overwriting the original executable's functionality in entirety. In this case, size of the shellcode and bad characters are typically not a concern. Now, the important thing is that in this series, we are going to concentrate on shellcode creation and not exploit research, which is a much larger and bigger topic. However, once we do other assembly language courses, I will launch a course entirely on exploit research on Linux and Windows, where you would get a taste for all of that. Shellcode resources. I think in my personal experience, shellstorm.org is probably the best place. You also have shellcode listed on ExploitDB and on Project Shellcode. Check out all of these resources. We'll be using some of the sample shellcode in some of our videos from these resources. So let me show you how one of these sites looks like. So this is shellstorm.org and this is the shellcode listing. If you notice, it's listed by operating system, and if you click on the Linux one, you would actually see a ton of Linux shellcodes available here for different purposes. The first one, for example, is for remote port forwarding. Second one is execv chmod on etc shadow. The third one is execv bin.sh shellcode. Let me open this up in a new tab. Now, basically, as I mentioned, shellcode is nothing but the end machine language, which is the opcodes of all the instructions which you're using. And this is where the author has specifically mentioned the instructions which he is using. This is an AT&T assembly, and then this is the finished shellcode for that assembly, right? So now the question really arises that while we are shellcoding, how do you test your shellcode, right? So to test our shell code, we need a skeleton program which eventually will pass control to our shell code to execute, and that would allow us to analyze if the shell code has properly executed and done its tasks or not. Now, the most common form of that program is a simple C file where basically you go ahead and define your shell code as an unsigned character array and then pass control to it. Now, here you may notice a lot of interesting pointer arithmetic happening, and what I'm going to do is I will not explain this from a C programming perspective. Rather, let's take an example shellcode from Shellcode Storm and then use it and then analyze what is happening in this program, right? So let's go to Shell Storm and let me copy this shellcode out. And I'm going to go to this program, and all of this, by the way, is defined or is available in SLE/shellcode directory. So you have shellcode.c. Now this is the place you need to place your shellcode in. Let me paste it in. There you go. Now let's compile the program. So we are disabling the stack protection as well as we specifically mentioned that we want the stack to be executable. Now these are just creating conditions so that our shell code can run without any problems. In a real world scenario, of course, the exploit conditions would dictate as to how you would do things like disabling dep and things like that, right? So let me compile this. And now let me run the shell code. And I'm just kind of hoping I have put this in correctly. Looks okay. Shellcode size mentioned here was 23 bytes. I think we missed a couple from what it looks like. Let me just copy this back again because our program says there are only 21 bytes. Seems to be wrong. Yes, I think we missed a couple of bytes in here while copying. Problem of copy pasting. I think 31C0 is what was missing. Sorry about that. Okay, this should fix it. Let me quickly compile this again. And there you go, we have our shell, right? Now, I could pretty much cut out some of the problems which happen when we do the videos, but they are intentionally kept in, right? The reason is not because I'm lazy to shoot it again. The reason is these are all smaller mistakes which happen while doing all of this, so you need to take care as much as I would need to take care of them, right? Anyway, so fantastic, we have a shell, right? So now let's go ahead and analyze how this little C program in here allowed us to test the shell code, right? So let me load up our little friend GDB in quiet mode. Set disassembly flavor to Intel. Let's break on main. Run the program, disassemble, right? So there's a bunch of things happening here. What we are interested in is, if I were to look at the C file, is really, when control eventually passes to code and this starts executing. Now, if you notice here in the top we really have a printf which is calculating string length, and a little bit of analysis would basically tell you that a bunch of stuff we are kind of doing in here allows us to figure out some of the things which we want. However, the interesting part kind of comes in here, which is call EAX. This is really the place where what is happening is we are going ahead and loading up the address of the location where our shellcode is stored, and we pass control to it. Now let's go ahead and print the address of code, right? This is the value, and if you notice, this is what is basically being moved onto the stack. And then after that, if you want to go ahead and notice what is kind of in there, you could basically go ahead and use the examine command. Multiple ways to do this. Let me go ahead and use the examine command, and let me give this address. And we have basically, if you kind of start noticing at this address, what you really have is this code all inverted. Can you see that? 31C05068, 31C05068. So really, if you go ahead and now disassemble, or sorry, go ahead and examine this in the form of individual bytes, let's do 23 of them, you would actually notice that this is exactly the location where our shellcode is, right? 31C05068, you have 31C05068, 2F, blah, blah, blah. And if you look at the disassembly, eventually call EAX basically calls this specific location. Let me set up a breakpoint in here so that we can ensure that that is exactly what is happening, which is our hypothesis is correct. We continue running the program. We've hit breakpoint 2. We are here right now, and if I now look at the contents of the EAX register, oops, you would notice that this is really nothing but the address of the location where our shellcode is loaded. So which means call EAX now would end up calling our shellcode, which would be this location. Let me set up a breakpoint for this place. Let me continue. Hit breakpoint 3. Now we are hitting disassemble, and now you would notice that this disassembly in here, XOR EAX, push EAX, blah blah blah, is really nothing but the shellcode, right? You have XOR EAX, push EAX. So this is in AT&T syntax, while the output which we see here is in Intel syntax, simply because that is what we told GDB to do. Fantastic. So now the rest of our shellcode goes ahead and executes and gives us a bin sh shell, right? Now in forthcoming videos, of course, you're going to learn how to create this shellcode on your own. Hopefully in this introduction video, two things are clear. What is shellcode, how it looks like, and how do you use the skeleton program which I showed to run and test your shellcode. And I would really recommend in the beginning to cut paste a lot of shellcode available on shellstorm.org to get a feel for what different shellcodes do. Of course, you're probably thinking it wouldn't be a really good idea to run other people's shellcode when machine code isn't entirely readable as to what is happening in the background, right? For all you know, it's a remove RF star shellcode. So run it in a sandbox. Hopefully most of the shellcode in Shellstorm, etc. has been tested. If not, definitely don't run it on a production machine. Run it inside a VM exactly the way which I am doing right now, right? Fantastic. So that's all for this video. Thank you. Welcome back. In this video, we will look at how to write shell code for the exit syscall. Now let's jump directly into the code. I am inside the shellcode exit directory. And let me open up exit.nasm, and this should be similar to what you've seen in the Hello World program. The exit syscall number is 1, which we move inside EAX. And if you want a non-zero return value, then you can put in any value apart from 0 in there. So I've kind of put in the value 10 inside EBX. Okay, so let's go ahead and compile it. And let's actually look at the machine code using a tool called object dump. Right, this allows us to dump the text segment, or all segments for that matter. We're only interested in the text segment right now. And if you notice, this in between here are actually the final opcodes, which basically are machine consumable. And on the right hand side is the disassembly, which of course is exactly similar to what is there in the exit shellcode.nasm file. Now this disassembly is in AT&T syntax, which is the default syntax of object dump. It's trivial to change that by using the capital M option. We use Intel, and now we see this being shown in Intel syntax. Now what one would need to do is copy this shellcode out and use it inside the file. So let me open up a new terminal or a new tab, shellcode.c, and let me start pasting this in. Now you're probably wondering that this shellcode has a lot of nulls in it. Why am I still using it? Just bear with me for a moment. I'd like to prove something to you. Copy the next line. And then we have CD80, and here we go, right? Now the point which I'm trying to illustrate is that the nulls being there in the shellcode is really a problem from an exploitation perspective. Now if you just transfer control to the code variable, this part here will execute in entirety. There is really no problem, and basically exit would happen, right? Now the removal of nulls is really due to the fact that an exploit might break. So as an example, strlen right now, which I kind of use to estimate the length of the shellcode, would break simply because it would encounter a null here pretty early. Let me illustrate that. Let me go ahead and quickly compile this in, and let me run this. And if you notice, it's run, we've exited as expected, and you could actually do an echo $? And see that the return value was actually 10, which is what was kind of put inside EBX, but the shellcode length just came out to be 2, simply because strlen kind of went ahead and only accepted these 2 bytes, right? So the key thing here is, remember, nulls like a binary is absolutely fine. Nulls in shellcode which you're using with an exploit may break the exploit, just like what you saw for strlen, right? So the next logical step, of course, is to remove these nulls. And if you look at basically the instructions, looks like move EAX01 has a problem with nulls, and so does move EBX, right? And It's kind of obvious. The reason is that EAX is a 32-bit register while 01 is a single byte value, and all the other nulls which you really see are just fillers for the other bytes or the other 3 bytes, similar to what is happening in here, right? So let's modify this shellcode and remove the nulls. So let me copy exit.nasm to exit no null.nasm. Let me open up exit no null.nasm. Now there are probably a billion ways by which you could avoid nulls. I'm just showing you one of the ways. Now the key thing to remember is that we just want to load the value 1, right? So you could just load AL with 1. But the fact remains that you still have the remaining 24 bits and they need to be cleared to 0 as well. Now moving 0 inside EAX before this would have exactly the same problem, which is there would be 4 nulls for all the 4 bytes which have been zeroed out. Which means we need to indirectly basically put a 0 inside the EAX register. The easiest way is to XOR the EAX register with itself, because we know that XOR of a value with itself is always 0. Now we can modify this instruction just to load the value 1 inside EAX. Similarly, we can do a XOR EBX and load BL with the value 10. Now if I were to compile this thing or assemble link it, and now use object dump, then you would notice that the resulting opcodes do not contain nulls anywhere. Fantastic. So let's copy these out into shellcode.c and verify the same. And as you're probably imagining, it's a stupid idea every time to cut, copy, paste. You'd probably end up more time cut, copying, pasting shellcode, which is of course error prone to begin with, than rather the shellcoding process itself. So we need some shortcut to convert the object dump shellcode into shellcode which is usable, right? Before we do all of this, let me summarize what we've done. We've ensured that EAX and EBX, which get used in the syscall, which were leading to zeros because of the values we load inside them, those instructions have changed, and this also makes our shellcode more compact. Now coming to extracting the object dump output and converting it directly to shellcode, we are going to use a little bit of command line foo, right? And there's a fantastic site called Command Line Foo where there are tons of quick command line shortcuts. You can use the link in the slides, and this is the one here: get all shellcode on binary file from object dump. And if you notice, this calls the -d option itself with a absolute fantastic looking combination of grep, cuts and sed and paste to do all the magic. So let me just copy this line out. I'm going to go in here, paste the line in, and if you notice we have a /program. I just need to change this with the executable we'd like to use. So it should be exit no null, that's the one. And fantastic, we have our shellcode exactly the way we want it. And if you notice, there are no nulls in it anymore. Go into shellcode.c, paste it in, compile it, run it. Fantastic, and exit happened. To an echo $? To figure that out, right? Now we used an $10 or the value 10 in our shellcode simply because we can identify that the program has really executed this part. But in reality, you would notice if you look at other shellcodes available, we really don't need to return a non-zero value. So this could be removed and further compact the shellcode. It's even more smaller, and you could use this version as well, right? Fantastic. And that's all for this video. Thank you, and see you in the next video. Bye-bye. Hello all, welcome back. Now in this video, let's try and write an interesting piece of shellcode. So in module 1, we looked at how to create a hello world program in assembly. How about creating a shellcode which prints hello world on the screen? And that's exactly what we are going to do in this video. The technique we will use to create this shellcode is called the jump call pop technique. And let's move ahead to understand more about it. Now what we are going to do is I will take the hello world program which was created in module 1 and first modify it to ensure that all 0 opcode instructions go away and are replaced, right? So all the move EAX, value 1 and all of that are replaced with equivalent instructions which don't end up with a null value in them. The second thing which is very, very important is that shellcode cannot have any hard-coded addresses. And the reason is simple. The same piece of shellcode is going to run in different environments within different programs depending on if you used it with an exploit or other circumstances. And if we hard-code addresses, those addresses would not be valid ones in all of those different circumstances. Hence, it is important that we dynamically figure out addresses inside our shellcode as and when necessary. And to do that, the technique we will use is called jump call pop, right? Now, let me go ahead and first get writing with the code before I show you what jump call pop is. Now I am inside the hello world directory which is inside the shellcode directory, and I'm just going to copy the hello world.asm file and rename it to hello world. Oops, too many spelling mistakes. Shellcode.nasm. Right, let me open this up. Hello world shellcode.nasm. This prints hello world onto the screen. This exits the program gracefully. Now the first thing, as I said, is I want to remove all instructions which end up creating null values in our shellcode. Now we already know many of these, so move EX4 is going to be modified with move ZOR EAX, move AL0x4, right? So this line goes off. Now move EBX01 again could be ZOR EBX or EBX, move BL0x1. Off you go. Now the next line is tricky. Move ECX message, which actually moves the address of hello world instruction inside the ECX register. So let's leave it aside for the time being. The next instruction is move EDX mlen. Now mlen is the length of this message. Hello world is 5, 10, 12, right? What I'm going to do is I'm going to add a new line at the end, which is 0xa, which makes it 13. I'm going to remove mlen here, and I'm going to replace move EDX mlen with ZOR EDX move DL 13, right? So this line goes off as well. And similarly for the exit routine, I'm going to do a ZOR EAX move AL0x1. Now EBX to return 5, let's just remove that and just return a 0 EBX, sorry. Right? So this is really the exact same form of the previous program, unless we've done any small mistakes here and there. And we should ideally verify this before we go further by assembling it and then running it. There you go, right? The program is exactly the same. So what we've done is, and let's actually verify this with object done to see that we've actually removed all nulls from it. There you go. And if you notice, all nulls have been removed, right? If you look at the disassembly in here, you would notice that inside ECX, we seem to be moving in this address, right? This is something which we don't desire. Now let's go ahead and remedy this, because if we use this in our shell code, it's not going to work, right? And why don't we just verify that in just a bit as well? Let me use the shortcut for dumping. Object dump into shell code. Let me copy this out. Let me paste the shell code in. And it's going to be run it. You'll notice that, well, nothing's happening. It's just printing something arbitrary based on in that program what is there in the address, right? Definitely not printing hello world. Now, of course, things could go further wrong, and you could have a seg fault and other things as well. So clearly this doesn't work. Let's go back to our assembly language program. Now the problem really is that we are trying to reference message with its address, right? And this is not desirable. What we want is that we should be able to figure out the address of message dynamically at runtime, and we just don't want to care how that address is going to change. So let's first make message the part of the code segment rather than it being part of the data segment for the time being. Then we go back to the presentation. Now, what is the jump call pop technique? Now, this is what jump call pop does. Remind yourself first of the call instruction and how it works. We said whenever we call a label, the next instruction after that call label instruction, the address of that next instruction is going to be pushed on the stack, right? That is the return address which is used once when we are inside the procedure called by call, we hit a ret and we would like to go back to executing the next instruction after call. So the jump call pop technique exploits this. How does it do that? First, it does a short jump, and remind yourself the best part about short jumps is they use offsets between -128 to +127. So there is really no hard-coded value, it's just an offset from the current location. So jump short call shellcode jumps to the call shellcode label, which ends up executing call shellcode. Now at this instance, we end up pushing the next instruction's address onto the stack. The next instruction basically is nothing but the address of the hello world string in the program. So the address of the hello world string gets pushed on the stack. Now, as soon as call shellcode executes, we jump control here to the shellcode label where we issue a pop ECX instruction. Now, a pop instruction is going to pop out a D word from the stack. And if you remember, the top of the stack currently contains the address of the hello world string, which is what goes inside the ECX register. And now we have the address of the hello world string inside our shellcode without having to explicitly hard code it. Fantastic. So let me go ahead and make those modifications. So here is what I'm going to do. Jump short call shellcode. Label this as shellcode. This is my call shellcode label, and I'm going to have a simple call shellcode in here. Right, and now ECX will basically get the value of the address of message by doing a pop ECX. That's all that is required. Right. Let me assemble and link this. Let me extract the shellcode. And of course, always before doing that, it's a good idea, as confident as you might be, to quickly do an object dump. And there does not seem to be any nulls in here. So we can safely copy the shellcode out, paste it inside shellcode.c. Compile, then run it, and there you go. Hello world now prints on the screen effortlessly. Fantastic. Now it doesn't end here. This is going to be a slightly longer video, so have some patience. Now our hypothesis of calling the jump call pop technique is something we would need to now verify ourselves using GDB. And my friends, this is exceptionally important. I think in the beginning you should verify the execution of every single piece of shellcode which you write or use by using GDB. So let me go ahead, load up GDB with shellcode, set disassembly to Intel, break main, run disassemble. I think if you remember from a previous video, the address really which we are interested in is right where code is located or where our shell code is located. That's something you can verify. So let me first print out the file once again. There it is, and now let me print out our shell code. Basically using, I don't remember how many bytes the shell code came out to be, just a second, 43 bytes. And if you kind of compare, you have EB7131 blah blah blah, EB7131 blah blah blah, ends in 64210A, 64210A, right? So we know that our shell code is there in memory. Just to verify this is exactly what you had in mind, which is the shell code is intact. You could even disassemble it, by the way, by using the I operation, which is basically examine as instruction, right? And if you notice, you have your jumps and your source and your pop ECX and all that stuff, right? And I think from this point onwards, this is nothing but hello world embedded just after your call instruction. right? And something you should verify as well. There you go. Right, remember, if you use this on other platforms and all of that, the exact addresses may be different when you kind of analyze it using GDB. Principle basically is just the same, right? Now let me set a breakpoint at the beginning of our shellcode, because that's what we want to analyze. We continue running the program. We hit our shellcode. Let me hit disassemble. Here is what it is, right? Now is the interesting part. Let the games begin, right? Let me go ahead and examine the data stuff which we are interested in. I think we are interested in how the top of the stack changes, right? Because we said that the call instruction which we have in here is going to push the next address, which is this value in here, onto the stack. So let's write a define hook stop disassemble, and let's just look at the top of the stack, $esp, and hit disassemble, and I'm basically going to do step I, and if you notice, the jump instruction was executed and this jump over here. Currently the top of the stack contains this value, but now once call gets executed, execution will go here. This is code +2 right here, but you would notice that the top of the stack would now contain the next instruction after call, which basically would have to point to this address, right? So this would get pushed on the stack. And if you notice, exactly that is what has happened. The address of the next instruction after call is now on the stack. So if I kind of go through this step by step, you would notice that after pop ECX is executed, ECX would contain the same value. So this is what is ECX right now, but after the next step I look at ECX, and this basically contains this value, which is nothing but pointing to our string hello world. Now the rest of this is something you're already familiar with, which is we call the syscall write and then the syscall exit. So you could just continue the program and get hello world as the output. Fantastic. Now guys, we are going to use the jump call technique, jump call pop technique over and over and over again, many times. So please ensure that you do the exact same analysis which I have shown you in this video. And till the time you aren't sure about all the moving parts, continue to run this again and again and again, right? This is a very critical concept. This needs to be understood perfectly, right? Do not try to memorize the exact flow. I can tell you it's easy to memorize, but it's not going to help you. In any custom situation, you would fail to think creatively out of the box. So spend your time in understanding why we are doing what we are doing and how basically the code executes in this whole jump call pop triangle, right? That's all for this video. Thank you. Hello all. In this video, we will look at a different way to write the same hello world shell code which we did with the jump call pop technique in the previous video. Now, the biggest issue which we faced in the last video was that we wanted to get a reference to the hello world string in the shell code, and we basically had to do jump call pop to push it on the stack and then pop it back from the stack, right? Now, the technique we will discuss in this video would involve pushing the hello world string itself on the stack dynamically and then using ESP to reference the hello world message and to use it along with the ECX register. Now, the important thing you need to remember though is that because the stack grows from high memory to low memory, you would have to push the hello world string in reverse order followed by a terminating null byte. So which means when we push it onto the stack, we would have to push in the null byte first, then the trailing /n, then the D, L, R, the O, W, the space, and so on and so forth. Right? This is the key catch in here, and if you understand this part, I think you would see that when we use the stack again for things like execv, shellcode, etc., all of that would be entirely clear. Now let's go into our machine, and what I'm going to do is I'm going to take up the previous program, which is hello world shellcode.nasm, and rename that to hello world shellcode, basically using the stack.nasm. You open that up. Now let's remove some of the things which are specific to jump call pop. Removing the comments as well. I think you pretty much know what to expect where. Now the important thing, if you note right now, is that the ECX register is the one where we need to go ahead and reference the hello world string. So there are two parts to the problem: A, to push the hello world string on the stack, and B, to get a reference to that string inside the ECX register. Okay, now if you recall, I said you would have to push the string in reverse order. How do we do that? Let's open a new tab, and I'm going to use Python to quickly reverse the string and to print it in hex. And again, shameless self-promotion. If you haven't seen the Security Tube Python scripting expert, definitely have a look at it. It's geared towards teaching Python, but from a pure InfoSec perspective. So basically this is what we have in here. So let me go ahead and define, let's say code equals hello world. Oops, I'm sorry. And now in Python, to reverse a string, it's extraordinarily simple. If you notice, now we've reversed it. You have /n, then the D, then the L, R, O, cap W, space, and then hello reverse, right? Now what I want to do is I want to convert these to hex. And in this example, the length has been chosen to be 12. So now I want to convert these into hex, so I can do an encode in hex format. There you go. Now, if you remember, the first thing which we need to push on the stack is a null byte. Now, you could do it in different ways. I'd prefer to just push an entire register in which has nulls in it. So let me first remove pop ECX. Now, I don't want to do a XOR ECX and use it again because that just increases the number of instructions. So I'm just going to use the EDX register to push 4 nulls on the stack. Okay, could push. So you're pushing 4 nulls on the stack. Now the next thing would be to push hello world in the reverse order. So we're going to have push 0x, and this is the hex equivalent. So let me pick up the first 4 bytes. Here they are. Picked it up. Push, done. Again, let's push the next 4 bytes on the stack. Should basically be 6F, 57, 20, 6F. So here is the next 4 bytes again on the stack. And then now let's finally push the last 4 ones on the stack. Yes, 6C, 6C, 65, 48. Here we go, right? Now, the top of the stack can be referenced by ESP, which is really the address where the string hello world starts from low memory to high memory. So all we really have to do is move ESP inside ECX. There you go. So now everything is set. EAX register is loaded with 4, EBX with 1, ECX is loaded with a reference of the string hello world, which is of size 12, and DL needs to be loaded with 12 rather than 13. I think the exclamation mark is something which we removed. Right? I leave it to you as an exercise when basically the number of bytes in the string is not divisible by 4, which is, it's like 13 or 14 or 15 or something like that. Right? So this looks pretty much okay to me. So let me go ahead, assemble and link it. Let me run it. Fantastic. Let me use object dump just to ensure that all the nulls are safely removed. Fantastic, no nulls. Finally, I'm going to use my little command line shortcut. This was hello world shellcode stack. Let's pick this up from here. Open up shellcode.c, paste it in here, compile shellcode.c. There you go. It prints hello world as desired. Fantastic, right? Now let's go ahead and analyze this. So again, this is going to be a slightly longer video. And what we really want to do is verify that, on the stacks, things are pushed really the way we are envisioning, right? So we love the Intel format. Let's break on main. Actually, we could just break directly on code, right, based on what we've learned in previous videos. So if you want to look at the location of code, here it is. As I said, multiple ways to set the breakpoint. Let's run the program and let's continue. We've hit breakpoint 2. Let's disassemble there. Here we go. So this is really the beginning of our shellcode. And if you notice, what we really want to track is how the stack is going to be set up right here, right? So let's go ahead and do that. Let me track the stack. Let me examine 20 bytes on the stack and print them as characters, right? If I remember, this is the right way to do it. Yep. Okay, so let's do the following. Let me define a hook stop where I disassemble and then I do the printing of the first 20 bytes on ESP and step I. Okay, so we could kind of sail in further till the time we don't hit the push instruction. There you go. Now what you would notice is that basically these 4 values, right, the first 4 values on the stack right now would just end up becoming zeros. There you go, right? We have 4 zeros on the stack, which happened because of pushing EDX. Now remember, we are pushing the hello world string in the reverse order. So because of the next instruction, we now see R, L, D /N. Awesome. Let's push in a little bit more. So now we have O followed by a space, W capital ORLD followed by /n, and then of course you have null. Last is when we push in HELLO as well. So now you have the whole hello world string on the stack. The next instruction basically ensures that ECX basically references the top of the stack at this point, right? Which is, it's now referencing the hello world string. The rest of the stuff is something you're already familiar with, so I think you could do it by yourself. Hello world is printed on the screen. Fantastic. So hopefully this technique is clear. The whole idea is to set up the stack in such a way that the string is there on the stack, and because we have control in figuring out the top of the stack using ESP, that's it, game over. Now keep these two techniques in mind in a very solid way. Most of the stuff would probably involve using one of these two techniques, right? Try this out, and I would really say, apart from hello world, try other strings, try strings which probably are not a multiple of 4, so that you would have to set up the stack in a slightly different way. And hopefully this video was crystal clear. That's all for this video. Thank you. Hello students, welcome back. Now in this video, we will look at how to create an execve shellcode using the jump call pop method. Now, before we really move on to the actual shell coding, the question arises, what is execve and what is its utility? Now, as you can imagine, a lot of times when we create shell code, you would want to execute some other program from within your shell code. So, you would want to locally get access to a shell prompt, or even remotely be able to access a shell prompt, as the most simplest example. So which means there has to be some way our shell code can execute the shell program on the system, which could be bin bash or bin sh or whatever is available. Now what this really means again is that we need to find a syscall which can allow us to execute a program from within our shell code. That syscall is execve. Now you can actually go to your system and do a man execve, and you would find the man page. Very simply, execve takes 3 arguments. The first argument is basically the program which you want to execute, and this is the absolute path, as an example, /bin/bash or /bin/sh. The second argv is actually an array of argument strings passed to the program, and quoting verbatim, by convention the first of the string should contain the file name associated. So in the simplest form, if you want to execute bin bash without any other arguments, then file name would basically point to bin/bash string in memory, while argv, the first element, would actually be the address of bin bash in memory, and the second argument would just be null or 4 zeros, to point out that it kind of ends argv there. Now the third argument is envp, which is nothing but an array of strings which you can pass in as an additional environment to the program before it is executed. Now typically we don't need to add anything new, so envp can pretty much be null, which is all zeros, or a d word 0. Going back to the slide, what does this mean? File name is pointing to bin bash null terminated in memory, and according to the syscall convention, this need to be inside the EBX register. argv contains basically two elements. The first is the address of bin bash in memory, which is identical to basically the pointer file name, and the second is nothing but null, which is a D word containing all zeros. And this specific combination of the first D word pointing to the address of containing the address of bin bash, and the second D word containing the null, this entire structure's address would be in the ECX register. Finally, envp just contains an address which points to null once again, and this would be in the EDX register. Now the most important thing, if you notice, that there are a ton of nulls in here which we need to have before we can execute or call execve. Unfortunately, your shell code cannot contain nulls, which means we will have to work around this restriction. Now, how are we going to do that? So let me go ahead and write some code. So I'm inside the execve folder. Let me copy our good friend template.nasm and call this execve.nasm. So open up execve.nasm. Let me remove all this stuff which we do not need. Great. Now let's go back to the slides. Now the first thing is we initially take a string which contains the program we want to execute, bin bash, and after that we have the next byte where we have a value a in it, and if you notice, this byte needs to be zeroed down to make a null so that bin bash is null terminated as a string. Then after that we are going to have 4 B's and then 4 C's. I'll come to why and what and etc. in just a bit. Let me define this in memory first. So I'm going to say message db bin bash, then you have a, b, 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 c, 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 c. Let's go back. Now the question arises that this string is contained in our shellcode. What that really means is, how do we go ahead and find out the address of the string in our shellcode? And to do this, we are going to use the jump call pop technique. Now remember, in this specific shellcode, EAX, EBX, ECX and EDX, all 4 are being used to set up the syscall. Hence, we cannot use any of these registers to point to the string. And what we will do is, we will use the ESI register. So let's now set up jump call pop in such a way that we pop the address of the string above into the ESI register. So let me go back in here and let's run the magic. So jump short call shellcode, and we go down in here. This is the call shellcode label, and we say call the shellcode. We go back in here, and this should be familiar because we've already looked at the jump call pop technique, right? And we basically say pop ESI. Now at this point, ESI contains the address of this specific string in memory, right? Let's go back to the slides. Now the second thing, as you're probably imagining, we would have to zero out A so that bin bash becomes null terminated. So we need to convert that A into a 0x0. How do we do that? So let's go ahead and first XOR a register with itself so that we go ahead and get a 0 inside it. So let's do a XOR EBX. Now we need to move the value 0x0, which can just be referenced by BL, into this exact position. Now the offset of this from the beginning of ESI is, you have 4, 5, 6, 7, 8, 9, right? So basically it's after 9. So we can do a move byte ESI plus 9, and BL would end up being the one moved there, and BL contains 0, which means that byte would now become a 0. Let's go back to the slides. Now there are two other things we need to set up in memory. The first is the address of this string bin bash null terminated has to be in memory somewhere, right? Now currently which register points to bin bash null terminated? ESI. So ESI, or the value inside ESI, needs to be stored in memory somewhere, and this is what we are going to overwrite the structure BBBB with, which is we will convert BBBB and store the address of bin bash, which basically is referenced by ESI. Fantastic. So I could simply do a move, and in this case we are moving an address, so it's going to be a D word, and say ESI plus, and there's just one A which we passed, so which basically means this is going to be 10, and what we move in is ESI, because ESI contains the address of the string bin bash. Let's go back. Now if you recall, argv required that we have two values one after the other. The first is a D word containing the address of the program to be executed, or basically the string defining the program name, which is basically what we've done and overwritten BBBB with. And the second was a D word containing nothing but null, right? So CCCC needs to get overwritten right now with all nulls, and we can easily do this by using the EBX register and say move D word ESI plus, and we can have gone 4 more bytes ahead, so this becomes 14, and we overwrite that with EBX, which is 0 because we XOR'd it there on top. Let's go back to the slides. There you go. Now if you look at this structure and if you compare it with what we require for execve, you would notice that we have all the elements in there. Now EBX needs to point to a string in memory, right, which is nothing but bin bash null terminated, which means EBX needs to contain the same value as ESI because that is already pointing to bin bash in memory. So for this we will use LEAs, or load effective address, as we've studied in previous videos. So we have LEA and EBX ESI. Fantastic. Let's go back to the slide. Now the second thing is argv, which is basically going to be loaded with using ECX. Now if you recall, argv is nothing but an address which points to a structure which contains the address of bin bash and then a null. Now this is really nothing but this location in here, and we've already done EBX, which is just after the null of bin bash. So if we go back in here, we already know that this is LEA and this is going to be inside ECX, and this would be loaded at ESI plus 10. The last argument, ENVP, basically needs to be an address which points to a null, and this is stored in EDX, and this can easily point to the last D word containing nulls. So purely by simple arithmetic, this is EDX, and this would be in ESI plus 14. Fantastic, right? Now, of course, after this, you would basically want to call the syscall itself. So we're going to do azor EAX, and the syscall number, which you should verify on your own for exec VE, is 0xb, and you have the syscall being called. Now the question arises, after this, do we need an exit routine? So if you actually do a man exec VE, if you notice, it says exec VE does not return on success and the text data BSS stack of the calling process are overwritten by the program which is loaded. Awesome. Which actually means, in reality, if exec VE succeeds, we really do not need an exit syscall to be there, which means we can avoid it. Fantastic. So this is all that is required to call exec VE. Let me go ahead and create the executable. Fantastic. Let me use object dump to check that we basically do not have any nulls in here. Seems to look okay. Right. Now, what you would actually notice is that if you run this, right, there's a segmentation fault. Now, I leave it to you as an interesting exercise to figure out why. A little hint, we are actively playing with instructions in the code segment where we are overwriting existing locations. That's the hint I'm giving you, right? Anyway, the good news is we could still use object dump to get the shellcode and load it up into shellcode.c, paste it in here, compile it, and run this. And if you notice right now, we have an additional bash prompt which is kind of come in, which is really the program which got executed, which is bin bash. Fantastic, right? You can exit, you can run the shellcode again, and there you go, right? And now you could play with this and use other shells also, by the way. So you could use execv.nasm. You could convert this to bin sh, just two lesser everywhere, which would actually mean this would be 7, this would be 8, this would be 12, which means this would be 12, oops, this would be 8, and this would be 12. Would this work? Tell me. I know I can't hear you, but would this work? I think in a real class, I could put all of these like interesting questions while I would be showing demos up there, and of course it would work. Why not? Right? So try out both of these. I leave analyzing with GDB to you. It's pretty straightforward. You would actually see that everything is getting modified just the way you'd kind of expect it to. I mean, it's kind of trivial. All you would need to do is track bin bash A, 4Bs, 4Cs, and see how it changes. right? So that's all for this video. Thank you very much. Hello students, welcome back. In this video, we will look at how to rewrite the execv shellcode using the stack method. So let's jump into our setup, and actually let me copy out execv.nasm into execv stack.nasm. Let's open it up. Oops. And let me rename the file. And let me remove all of this from here entirely first, right? We really don't need any of this. All I really want is the skeleton, so that we always have the same common starting point. Okay. Now remind yourself of the stack method which I demoed to you for Hello World, right? The Hello World shellcode. Now there are a bunch of things which you'd probably remember from the previous video. We're going to take you back. Probably this screen would be the one which is most important. Okay. If you remember, the EBX register would need to point to bin bash. The ECX register would need to point to argv, and the EDX register would need to point to envp, right? And this were really the values which we wanted to put in all of those locations. Now I'm trying to create this exact same setup using the stack. The key difference here will be, rather than pushing them in this specific order as you currently see, I'm going to push them in a different order and then point the appropriate registers in such a way so that this condition which we had taken in the previous video about EBX pointing to bin bash, ECX pointing to argv, and EDX pointing to envp is valid. So now let me come back in here. Okay, so stack, as we know, grows from high memory to low memory. The first thing we are going to push on the stack is a D word, which is just nulls. Now let me go ahead and write the code as we go ahead and do this, right? So in order to do that, multiple ways, I could just zor EAX and push EAX onto the stack. Fantastic. Let's go back. Now the next thing I want to push is basically the string bin bash on the stack. So let's go back in here. Let me open up a new terminal because I want to show you something else before we go there. Okay, now if you look at /bin/bash, this is basically 9 characters, right? And if you execute it, of course, you're going to get a new bash prompt. Now, if you remember, we typically want the pushes to be kind of aligned with 4 or multiples of 4, right? Which is, we would actually want to go ahead and put in 12 instead of 9 characters. It makes it easy to just use a couple of pushes. Now, there are multiple ways, of course, in which you could just put in 9 and then you could figure out other instructions with which you could ensure that everything works. But that would increase the number of opcodes in the final shellcode. This is where a common trick is used by shellcoders, which is whenever you run a program by giving its path, the number of slashes in there does not really matter. What do I mean by that? Well, you could invoke bin bash like this, or let me actually invoke bin sh so that we clearly see a difference. So this is bin sh, but you could also add an extra slash and invoke it like this. Frankly, you could add as many as you like, right? It has the exact same effect as far as execution, interpretation and execution of this string is concerned. So this is what we are going to use. Rather than using just simply bin bash, I'm going to go ahead and add 3 more of them, 10, 11 and 12, And this is exactly the string which we now want to push exactly in reverse direction like we had seen in previous videos. Now you could use Python and all of that stuff as I'd shown you previously, but me being really lazy, I've written a very simple program to do all of that in just a jiffy. So you have reverse, and after that feed it the string. So we had 4 bin/bash, and if it says string length is 12, you're good, it's a multiple of 4. And if you notice, it already tells you what you need to push in reverse order, right? Simple little script, but comes in really handy when you want to play along with the stack method for writing shellcode. So I'm going to push these 3 onto the stack first. Let me go back in here, copy this out. And of course, you could have redistributed the slashes between the 2 original ones which were there. Here comes the final one. There we go. Let me go back to the slides. Now, if you notice, this is nothing but bin bash null terminated. And bin bash null terminated needs to be there where? Inside the EBX register, the address to this location. Now, what is the register which currently points to the beginning of the bin bash string? ESP, right? Because we are pushing all of this on stack. So to get that inside EBX, we use the simple move instruction EBX ESP. Fantastic. Now let me go back here. Now what we're going to do is we're going to push another null in, and if you remember, envp actually needs to point to a null in memory, and envp needs to be there in the edx register. So we will push a null and then save esi into edx. So here goes, we again push eax, and then I'm just going to move edx esp. Right? Fantastic. And guys, it's probably a good idea also to kind of comment everything in, I'm leaving the comments to you, so it's like, push the first null d word, whatever you'd like to write here. Push bin bash 12, so you remember why you did that, and so on and so forth. I kind of leave it to you. When you practice the code, it's probably a good idea that you should write the comments, at least in the beginning. Now, what remains is basically argv, which is supposed to point to the location where we have the address in the first d word and the null in the second d word, right? So I'm going to push the address of this location stored on EBX on the stack, which is very simple because it's already in EBX. So all I do is a push EBX, and then once that is done, I just move the top of the stack onto the ECX register. So here goes move ECX ESP. There you go. Right? Now, all I need to do after this is call the syscall. So you have move AL either 0B or 11, whatever you like, int 0x80, which is basically CD80 in opcode, to call the syscall execve, which should do rest of the stuff, right? Fantastic. Now let's go ahead and assemble and link this. Awesome. Here we go. And if you notice, execution happened, right? Which means everything is absolutely fine. Quick look with object dump. So that we are sure there are no nulls which have kind of crept in anywhere. And of course, when you do exploit research, probably any of the other disallowed bad characters as well. Fantastic. This calls for a cut. Exec v stack. We have our beautiful little shellcode in here. Copy it out. Open up shellcode.c. Paste it in. Compile. Oops. Run the shellcode. And there we go. Right? Awesome. And to be honest, you could just play around with this right now. So instead, if you wanted bin sh, all you would basically have to do is replace the little pushes in here with bin sh, which would mean you could just go in here and do first check how much characters bin sh occupies by itself. It's already 7. You could add one here as well. This makes it 8. And here you go. You just need to copy this out. Right? Go in here. Let me just uncomment this out rather than like changing it or deleting it entirely, so that you guys can use it for a reference later on when you want to have a look at my code. Right, we copy this out. Paste it in here. The best part, if you notice, everything else is like just taken care by itself, in the sense there is no dependence really on the size of what we are pushing, right? Which is the string here which you're pushing in can actually be arbitrarily long. Okay, you can just go back in here, run all the commands once again, verify that this works. Does work. Cut, get the shell code. And to be honest, even this whole process can be automated, which is, you're going ahead and writing a script which first of all links, assembles, calls object dump so that you can quickly grep and check if there are any nulls or not. If no nulls, then go ahead, use the whole long expression to cut, generate the shellcode, and then paste it automatically inside shellcode.c, compile it, and then run it, right? That will save you a lot of time. The reason I personally like to go through this, because while teaching, I want you to be aware of all of these steps. Because frankly, it's the exact same steps each and every time you want to play with shellcode, right? These steps should be in your mind. You should never ever forget any of them. There you go. Run this, and here we are. Now, even though people show bin sh and bin bash with shellcode most of the time, well, exec-v pretty much allows you to run anything, right? The case which we are working with right now is exec-v, which is calling any other program but not passing any other arguments. Because if you remember, if you want to pass other arguments, you need to extend argv. Then argv would first contain the address of the program's name which you want to execute, then all the argument addresses, and then finally the null, right? So I leave it to you as an exercise to give arguments and things like that. It's pretty straightforward. It's just on the same line. The only thing I want to kind of put it in your mind is pretty much you can execute any program you like. So let's say you wanted to just, do an ls in the current directory. You could pretty much do that as well. So from what I remember, it is in bin ls. Yep. So I could just call my little program here again and say bin ls7. So I could just say, hey, here's my next slash 8. And you could pretty much copy this. Right, let me comment out these lines as well, so you can try out all of these later on your own. Now, interesting things could be done here. For example, if you look at Shellstorm, you will see a lot of code which says IP tables flush, which is like clearing IP tables and stuff like that, which you could use. Basically, what the shell code is really helping you do is pretty much run any command you want on the remote system, which is available. Right, so let's try if I execute this. Actually, see, I just did an ls on the same directory. And you could pretty much, do an object dump cut and then paste it inside shellcode.c, and it would run as well. Hopefully you figured out why I was able to run execve-stack without any worries, while the plain execve is used jump call pop had a segmentation fault, right? It's important you understand that on your own, because there has to be some self-exploration as well. Okay guys, so I think we've had a lot of fun in this video. I'll see you in the next one. Take care, bye-bye. Hello students, welcome to part 7 of module 2. Now in this video, we will start working with our first encoder decoder, which is the XOR operation. Now XOR, as many of you already know, is actually a very simple operation and it operates on individual bits. The whole idea is that if you have two quantities A and B, then A XOR B would be 0 if both A and B are 0, would be 0 again if both the quantities are again 1, which is A is 1 and B is 1, and would be 1 in other cases. So in reality, A XOR B is 0 if both A and B are same, while it would be 1 if one of them is 1 and the other is 0. Interestingly, if you do the math, A XOR B, the result of this XORed again with B gives us back A. And this is a very interesting property, because what this means is that we can reverse a XOR operation by ensuring that we XOR it again, the result with the same quantity. Now, what does this mean for us? Well, we can select, in the most simplest case, a single encoder byte, let's say 0xAA, and XOR every byte of the shellcode with 0xAA. Now, this would give us an output encoded shellcode, and then we would need to write a decoder stub which would XOR this encoded shellcode again with 0xAA on a byte by byte basis, and this would give us back the original shellcode. Now once the decoder recovers the original shellcode, all it has to do is pass control to the decoded original shellcode, and that's it. Your shellcode runs just as before. Now what do I mean by that? Right? Too much text can kill stuff. So simple visualization. We have an original shellcode, let's say, 20, 30, 40, how many ever bytes. I've just taken the first 4 and given a dot dot to show that it's a large array. And let's say we want to do a XOR with the byte AA. So what we do is we do basically a byte by byte XORing, and we get an output, and this is basically the encoded shellcode, right? Now in the program, what we do is we write a decoder stub, and in the most common case prepend it to the encoded shellcode, And what this decoder stub does is it works on the shell code and decodes it in memory to give us back the original shell code. Now, after this is done, the decoder stub passes control to the original shell code which has been decoded now, and then our original shell code runs. So now let's go ahead and do all of this in a step-by-step way. So let's go into our lab machine. Now I would want to use some of the shell code which we've already created so that we would encode it. So let me copy out the execve shellcode. Let's say I use the execve stack.nasm file. Let me copy it in here. Let me open it up. And the one which I'd really be interested in using, let's say, is bin.sh. So let me just remove all of this other stuff in here, right? Which may end up confusing us. So only bin.sh remains. Everything else is removed, right? Let me go ahead and get the output. Let me ensure that this really runs as desired. It does. Now let me go ahead and extract the shell code from this. So I'm going to do an execve stack, get the shell code out. Let's quickly verify that the shell code works. Yep, shellcode works perfectly. Now what we need to do, if you kind of remember from the slide, is XOR the original shell code with AAs on a byte by byte basis, right? So what I've done is I've written a very simple Python script where I can paste in the shell code, and this is something of course you can use as well. And what we do in here after this is we iterate through the shell code as a byte array, and for every single byte we basically do our XOR operation with AA, and after that I'm just aggregating the result in two variables and I'm printing both of them, right? Awesome. Now the only thing you need to remember is that the byte value you're using to XOR encode cannot be something which already exists in the shellcode. And the reason is XORing the encoder byte with itself would result in a 0, and that would not be a permissible value which you can use in your encoded shellcode. So that is the only thing you need to quickly verify, which seems okay in this case. And now let me run my XOR encoder. So it gives me the output in two different versions. This one is easier to use with NASM. So let me use this one. Copy it out in here. And now what I'm going to do is, let me go ahead and use execve stack.nasm. Let me copy this out to XOR decoder.nasm. Right? You open this up, XOR decoder.nasm. Name the file accordingly so you can remember later. XOR decoder. And in reality, all I said I needed was really the skeleton on top, because I'm lazy. Pretty much remove everything else. Now let me first paste in the shell code. There we go. Now what I'm going to do is I am basically going to write the decoder stub. Right, the next step is my encoded shellcode is now in. I need to write my decoder stub. Now the decoder stub would basically go ahead and XOR each and every byte of the encoded shell code with 0xAA once again, right? So of course, the first thing your decoder would require is to figure out where exactly is your shellcode sitting in the program memory. And we will now use the same jump call pop technique to find this out. So let me write out the skeleton. Jump short call decoder. Oops. Decoder is in here. And this would be my call decoder. Here is the actual call instruction. And by the way, if any of this is not clear, you probably need to visit all the other videos which we've done, right? We've explained this time and again how jump call pop works. Now, we can get the address of shellcode by simply doing a pop on any of the registers. Let's do pop ESI. Now, if you go ahead and look at the length of the shellcode, the length of the shellcode has been given as 25, right? Which means we need to basically start here and go 25 times with our XOR operation, right? So this is exactly what we are going to do right now. And I'm going to use the loop instruction, which means I need to load up the ECX register with 25. So XOR ECX, ECX, move CL25. And now comes the real loop, which let's just call this decode as the label. And very simple, XOR byte pointed by ESI along with 0xAA. That's it. And then you simply increment ESI and we loop over this, right? Loop decode. And what this means is after 25 we would come out of the loop, and all we need to do is jump short. And what did I name the shellcode? It's just shellcode, so it's basically jump short shellcode. Here we go, right? So very simple. We jump short to call decoder. We come in here, call decoder is hit, which means now the address of shellcode is on the stack. Decoder is in here. We pop the address of shellcode to ESI. We know the length of the shellcode we want to decode is 25. So we set up ECX with 25. And then we move into a decode loop where we basically XOR each of these bytes with AA, increment ESI, and then loop around that for 25 times. Once we come out of the loop, we know that this shellcode has been decoded, right? And at that point, we basically jump to this shellcode. Fantastic. Let me go ahead and get this all together. Everything looks okay. Let's use object dump just to verify that we don't have any nulls in there anywhere. Okay, no nulls, fantastic. Let's extract the shellcode now. So shellcode.c. Let's paste our shellcode in here. Compile this. And perfect, right? Awesome. So now you have the XOR decoder which decodes the encoded shellcode and then passes control to it. Fantastic. Now, before I move into an analysis with GDB, we could do one small modification, or you could just rewrite the decoder in a slightly different way. How is that? Well, one of the things which we had done was that we went ahead and statically passed the length of the shellcode. Alternately, we could have used some kind of marker. What do I mean by that? Let me just copy zor decoder.nasm to zor decoder marker.nasm. Open that up. And what I'm going to do is going to go down here, and at the end of the shell code I'm just going to add 0xAA. Now what is going to happen? Well, if we did not have the whole zor ECX loop and all that stuff, we could just remove this. What we could just go ahead and do is keep zoring each of these value with AA, and the moment the zor ends up in a 0 value, we know that we've hit the last byte, right? Because 0xAA is going to be the marker, and that's exactly what I'm going to do here. I could just remove all of this from here, and I could say, you're right, if this ends up in a 0, jump to shellcode. And of course, if that really isn't happening, then sure, go ahead, increment ESI as usual, and jump short to decode. Right, so now what happens is we keep moving along this whole length of the encoded shellcode. Finally, when we hit this value, the zor ends up in a 0 value, and that sets the 0 flag, and hence JZ shellcode is hit and our transfer goes here, right? If not, we keep incrementing ESI and keep decoding more and more of the encoded shellcode. So I'm just trying to iterate that really there is no one specific way you need to kind of approach the problem, right? And to be honest, as I'll tell you in the next video, using all the well-known techniques of encoding is actually useless, because you wouldn't be able to obfuscate from IDSs or AVs or anything like that, because all of them are aware of the known techniques. There you go. Now what I'm going to do is, let me go ahead and get the shellcode out from in here. Paste it in shellcode.c. Compile, run, and there we go, right? Just another way of going ahead and doing it. So the shellcode length was 42, and I think the last time it was 45, right? So we've now ended up reducing 3 bytes, which in the shellcode world is pretty good. Okay. So we've had all of this fun. Now let's try and analyze the shellcode using GDB, right? Because what I really want is, I would like to see the decoding happening in real time, right? That would really be fun. So let me do the following. Let me load this up in GDB. And the one which is currently inside shellcode is basically the modified one where we are using JZ, by the way, right? Keep that in mind. And really all you want is print/x ampersand code, and basically we just want to set a breakpoint for this value. And again guys, if any of this is confusing about why this value is being chosen, I think you need to go back and visit previous videos while I've explained how all of this is done, right? run. We've hit the breakpoint, disassemble. Here we are, right at the beginning of our shellcode. Now, if you notice, basically the place from where our shellcode really starts is here. And we could figure that out. Let's just go ahead and shell cat shellcode.c so that we see our shellcode. And then I'm just going to do an byte by byte, 45 for individual bytes. Then I'm coming in here and just below the call instruction, let me get this address, copy it in, paste it. And if you notice, this is really where the shellcode starts if kind of put in everything properly. Okay, this is really the whole encoder block and all of that together, which basically means it starts from somewhere in here, right? This is our encoded shellcode. It starts in here and goes to AA, and this is exactly what we are seeing in here, up to AA. Here we go. Right? So we really want to watch this and see, what is happening in here, right? So couple of things which we can do. The other thing, of course, is to also see how the instructions change after the disassembly, or sorry, the decoding happens, which means you could also do an x/i on the same address value, which right now, of course, is all gibberish. I mean, this doesn't make sense because we are trying to interpret the encoded part of the shellcode, and of course all the stuff from here to till before 9b, right, is really the encoder stub. Okay, so now let me just quickly write a define hook stop disassemble x/, let me just do for small values, then we just extrapolate it for others, and x/10. Oops, small mistake, forgot to give the exact location where I wanted everything to happen. There we go. And disassemble step I. Right. Now let's basically keep moving forward. Really what we want is, once we are going to come into this whole loop, right? So just keep moving forward. So here is where the XOR is going to happen in the next step. And that is exactly what we'd like to see. What happens, right? The XOR is the next operation now. And let me actually keep stepping through it a little bit more. Right, and if you notice, if you kind of go in here, the XOR is now continuing. So what I really want is, as soon as this hits, which is basically everything is kind of done, right, we would basically go out of the loop, and then we would end up calling this part in here, and this is really the place which you're kind of looking at, right? As soon as all the shellcode decoding is kind of done, you would want to go ahead and inspect it. So let's do the following. What you would like to do is we'd like to get the address which we were tracing for such a long time, and that address, I guess, is in here, and you could just scroll up and verify that once again. This is really the address we were kind of looking at, and I'm just going to set a breakpoint for that address, because I know as soon as my shell coding decoding happens, that's where the control goes. Continue. Right, and now notice something extremely interesting, right? We've hit the breakpoint, and if I do a disassemble, you would actually notice that all that gibberish down below which was there is now fantastically decoded into what? Our original execve-stack.nasm shellcode. Can you see that? Right? So all of that has now been decoded, and then the control has been passed to this location from here. Right? JE got hit, control is passed here, and now all of this code which you have in here is basically exactly what we wrote in execve-stack.nasm. Oops. There you go. This is really all the code, right? And if you kind of scroll up here, this is exactly what you have here. Which means, awesome, our decoding has happened, and now control has been pushed to our shell code after the decoder stub, which is basically up till here, has done its magic. So now we can just continue, and basically we get a shell which you can exit, right? So hopefully now all of these steps are clear, and I would really encourage you to use GDB to go through this exactly the way which I have done. The best part is that once you understand how the decoding and all of that happens, and you're able to trace through all of that, you would practically be able to understand most other decoders out there, right? Anyway, hopefully you've enjoyed this video. This was fun. It's a long video, I know that, but I wanted to do this in just one sitting. So that's all for this video. Thank you. Hello students, welcome to video 8 of module 2, and in this video we will look at how to use encoders within Metasploit. Now Metasploit is a versatile tool with which you can do vulnerability assessment. It can help you in exploit research, and specifically for our purpose it can help us create arbitrary payloads as well as to encode payloads with different encoders. Now, in order to look at all existing payloads in Metasploit, of course, the first thing you would have to do is install Metasploit. Now, please download the latest version of the Linux installer from their website and run and install it. I leave this as an exercise to you because it's too simple. Inside the directory download which you would get for the code, I would not include the installer simply because it's too large, and I don't know if their licensing even allows me to redistribute. Anyway, should be easy to download and install by yourself. Now, if you wanted to look at all the different payloads offered by Metasploit, we can use the MSF payload utility which ships with it and pass it the -L option and basically grep for Linux x86. Now there are three utilities. You have MSF payload, MSF encode, and MSF venom, which basically combines payload and MSF encode, right? However, I'm going to be using payload and encode separately. Now, as you can clearly see here, you have all of these different payloads available, and you can go ahead and create shell code for any of these and use it in your programs. Now, I will look at disassembling MSF payload outputs in a later video where we are going to look at how to disassemble, understand, and analyze shell code which you may receive. In this video, what I want to focus on is, if you create your own shell code, how can you use the different encoders in Metasploit to encode it without having to write your own encoders for the job. So what I've done is I have the execve stack.nasm copied into this directory, and what I've done is I've enabled the push bin sh1 as the active execve command which you'd like to run. Let me go ahead, assemble, link it. Here is the shell code. Copy it out. Compile and execute. Of course, we get a bin sh shell as expected. Now, this shell code right now is basically in its purest form, in the sense all it does is an execv using the stack method and execs bin sh. Now, what if I wanted to encode this using one of Metasploit's encoders? Now, the first thing I'm going to do is list all the encoders which are available with the -L option to MSF encode. And I have a ton of them. The ones I'm interested in is down here, x86, right? So some of you may already recall, if you ever used Metasploit, Shikataga 9 is available here, and a bunch of these other encoding techniques. And because Metasploit is open source, you can go have a look at the code and how it's been created as well. Let me use the jump call additive method as an example. Copy this encoding technique. And what I really want to do right now is to go ahead and use this shell code and encode it, right? So here is how I'm going to do it. I'm going to use the echo command with the any option, paste the shellcode in here, pipe it to MSF encode, and then give it the option -a x86. This is the architecture. The output I would want in the form of a C array so that I can use it in shellcode.c. And the encoder I would like to use is, go up, x86 jump call additive, copy and paste it, right? And here we go. Okay, so this gives us an output which, as you can clearly see, is larger than the shell code we pasted in. Let's copy this, open up shellcode.c, paste it, compile, run the shellcode, and there we go. Fantastic, right? So now we encoded our execve bin sh shell code using the jump call additive encoder from Metasploit. Now let's try a different encoder, the one I think many of you have probably used, the Shikataga 9. One of the other things which you can actually do is encode multiple times. So basically the output of 1 becomes the input to the next encoding cycle. Let's do it 10 times, right? This will actually give you a larger shell code, because the more number of times you kind of encode it, you have more and more code getting added. Let's copy this. Shellcode.c. Compile, run, and works fantastically, right? A small variation, as we discussed in the delivery of shellcode, is actually to push this shellcode into an executable, right? That's something you can do trivially as well. Basically, instead of the -tc option, basically give elf executable as the option and store the output in a file called demo. So what this does is, now the shell code which comes out, it basically converts that into an elf binary. So if you do a file demo, you'd actually see that it's a 32-bit elf. You could make it executable, and if you execute it, there you go, you get your shell, which is another variation of the whole process. Now, if you were really curious about how the shell coding and all of that is really working, you could basically either look at the source code in Metasploit, or you could load up the shell code, as you know, the shell code binary inside GDB, and break at code variable whenever we start executing our shell code. Set disassembly flavor Intel, run, hit the beginning of our shell code, and there you go, right? So the Shikataga 9 is actually using the FPU instruction set here and there as well, which you can clearly see at the top. And then you can trace through and figure out what is happening. Of course, right now we have multiple iterations, I think over 10, so probably just having a single iteration would be better if you wanted to trace along and look at how Shikataga 9 really works, because 10 iterations would be exceedingly complicated to go through. Coming back to our slides. So there are multiple encoders. The best part is that you don't need to rewrite the source code of every single encoder like the way we did for XOR. No point reinventing the wheel. You could do it if you just want to learn how to write more encoders, and I'd recommend looking at the source code or looking at the shellcode output and tracing through how the encoder works. So we've leveraged Metasploit to create our own shellcode with the help of MSF payload, which I'll show you later, or to encode your own shellcode, or to dump it in a binary and execute. Now, the key thing I'd like to point out is, as far as AV and IDS evasion and things like that go, a lot of people tout encoding as a very effective way, but unfortunately, most existing encoders in Metasploit are very well known and documented, which means most AV and IDS companies may have anti-evasion kind of techniques built in to fingerprint these encoded shellcodes. The most common part they end up fingerprinting is actually the encoder stub, right, which is required to decode the encoded shellcode. So they aren't really very useful, apart from probably Shikataga 9, because it's a polymorphic encoder. It does work at times, but not reliably always. So what I'm really trying to say is, there are tons of existing encoders, but in reality, if you really wanted to do evasion or something else with these encoders, they might not be very useful or helpful to you. And that's the reason why I see no point in repeating, okay, this is how the jump call additive encoder works, this is how this works. Wouldn't serve much of a purpose. Now, what we would need to instead focus is on how to write your own custom encoder, right? Now, there are two things I'd like to mention. It's exceptionally easy to write a custom encoder and bypass AVs or other things till the time the technique is not disclosed or the AV manufacturers do not know about it, right? And why do I say this is easy? Because an encoder is simply a mathematical function which transforms your shellcode from one form to the other, and the decoder just transforms it back to the original version and executes it, right? Any such mathematical function which either changes every byte of the shellcode or scrambles the shellcode so that you can unscramble it later would work, right? However trivial that mathematical function might be. And unless the AV is really smart, tries to go ahead and simulate what is happening in the executable, it might not be able to catch the actual shell code where you may have any of your malicious tasks happening, such as deleting all files or creating a backdoor or whatever. Now, the corollary really is it's exceptionally difficult to write an encoder whose method is public and still continue to evade AVs or IDSs for that matter. And the only one which is even reasonably close to probably doing this even till date is the Shikata Ganai, right? Now, what I would like to do is, rather than looking at very complicated examples, in the next couple of videos, I'd like to show you simple ways purely based on your imagination on how you could create different encoder techniques. And that's really all I have in mind for this video. Try out with Metasploit, look at all the different encoding types or the encoders which are there, and from the next video I'll show you how to begin with writing your own encoders based on any creative idea which you may have, right? That's all for this video. Thank you. Hello students, in this video we will take up our very first custom encoder, which is going to be a very simple NOT encoder. Now, what is a NOT encoder? Well, it transforms every byte in your shellcode using the NOT operation, and as you're probably already realizing, the decoder will basically NOT the encoded byte to get back the original byte, and then it will pass control to all bytes after the decoding happens and your original shell code runs. So let me go into our little directory. What I'm going to do is, first let me copy some of the shell code which we have been using. So let's say let me copy out the execv stack.nasm file in here so that we have some shell code to work with. So we could use this, and just to verify that everything is fine, let's go ahead and delete this, paste the shellcode in, compile and execute. Shellcode works fine, right? Now the first thing I would need, of course, is my NOT encoder. And I've written that in a very simple encoder.py file. And all this does is it complements and then it prints it in a format which we can use. So let me copy this shellcode which we have in here into that file. Let me get the not encoded output. The length is 25. Let me copy this out. And of course, once again, all you need to quickly check for is that there are no zeros in your shellcode anywhere, no nulls, which is okay in here. And now let's write our not decoder. So let me copy this in here. Encoded shellcode, define byte. Let me paste it in. Now I'm going to use the jump call pop to find the address of the encoded shellcode. So we have jump short call shellcode. This is basically going to be my decoder. Current call this as decode, and here is my call underscore shellcode, under which I have my call decoder. Right, in decoder I want to get the address of encoded shellcode. That's done with a simple pop ESI. And now in the decode part, basically I want to knot it back to get the original shellcode, right? Now if you remember, the length of the shellcode which we had seen was 25. So let me run a loop for the decode, for which I'm going to use the ECX register. And the decode part itself is going to be really very simple. Just a plain not byte pointed by ESI, increment ESI, and then finally just to loop for 25 times. So we have loop decode. And I think after we come out of this loop, we just want to do a jump short encoded shellcode, right? Looks fine to me. Let's try and run this. Looks okay. Let's run object dump just so we are sure there are no nulls anywhere. Okay, no nulls. Let's paste this in shellcode.c. Compile, then execute. There you go. Our not decoder works perfectly. Let's quickly use GDB to analyze the whole situation. Right? Now, if you kind of notice, we have our jump in here, we have a call in here, which means this point onwards is where our encoded or not encoded shellcode has been put, right? We can go ahead and verify that. So let's call shellcat in not encoded.nasm. So this basically starts at CE, and if I go ahead and do an x20xb and basically get the next address after the call instruction, There you go. Right, so you have your CE3F etc., which is your not encoded shellcode. So what we really want is, if I go back and hit disassemble once again, after this loop is going to end, I would like to again look at these values right down here and see if it has been disassembled to my bin sh shellcode. So let's do the following. Before the disassembly, or before the decoding has happened, let me look at these from an instruction perspective in here, which of course is already something you can see on the screen. But let me just use the examine command to do it, which clearly doesn't make any sense right now because, you know, all of this is just bogus. It's all encoded. Now, here is what I'm going to do. I'm going to set a breakpoint just after the loop instruction ends, which is in here. So we know when we hit this location in execution, we know that our encoded shellcode has been decoded entirely. So let's continue. We've hit the breakpoint, hit disassemble, and can actually see it from here itself. This whole part in here has now been entirely decoded. What was previously basically this part in here is now being decoded entirely to our bin sh calling shellcode. Fantastic. And now the next instruction would basically pass control to our shellcode, the decoded one in memory, and after this you would have bin sh executing just as you would expect. Right? So if you continue execution, you basically get your shell, and there we go. Fantastic. So I think this was a very simple technique really, but what I wanted to show you is that's it. I mean, you could get more and more creative, and basically there are two ways. One is you transform using a mathematical function, or B, you just scramble the whole shellcode and then have an unscrambling function so that it gets back to the way it was oriented before, right? So try this out. That's all for this video. In the next video, we'll try and be a little bit more creative and see what other things we can do with our own custom encoder. Thank you and have a great day ahead. Hello students, welcome to part 10 of module 2. Now in this video, we'll try and write another custom encoder which I call the insertion encoder. Now what is really the insertion encoder? So let's say this is how our original shellcode looks like. In the case of an insertion encoder, I basically insert an absolute garbage byte, right, between every 2 bytes of the original shellcode. So you can actually see AA in between every 2 bytes of the original shellcode. Now variations of this can be, instead of AA, you could have a random value, or you could probably have an increasing sequence and things like that, right? So the basic idea is that there is garbage, and this would end up probably confusing a lot of AV and IDS systems. Now, how do we go ahead and write a decoder for this? So the idea is again similar to what we've done in previous videos, which is write an insertion decoder stub. And what that stub would do is that it would take, let's say, the next legit value of the shellcode, which is AB, and then put it in this location where the first garbage value is. Then it would take the value of AC and then put it to the place where AB is. It would take the value 0, 1 and put it in AA, right? So that what is happening is the original shellcode is now moving at the absolute front, and we are overwriting all the values and ensuring that no garbage value now exists in between. Once this whole process is complete, just like in previous cases, we send control to the beginning of the original decoded shellcode. So let's go ahead and do this. Now I have written a very simple Python script to do the insertion encoder, and all it really does is it will take a piece of shellcode and insert 0xAA after every byte of the shellcode. Now in the same directory I already have execv stack.nasm. This is exactly similar to what we've encountered in previous videos. I'm going to cut that out. So I'm going to have basically execv stack, copy this out. Let's just quickly verify that the shellcode works. Let me paste it into shellcode.c, compile, execute, and it works perfectly, right? Shellcode length is 25. Now I'm going to take the same shellcode and paste it inside our Python script. And run the Python script. And this is going to give us the new shellcode which has 0xAA inserted in every even location. So now the length of this shellcode is actually 50, right? Because the original shellcode length was 25. Now let me actually write the whole decoder program. So let me call it insertion decoder dot. Let me actually copy out the template just like I do for every other video. It's just easier to work that way. Template.nasm, and let's call it insertion decoder.nasm. Open it up. Insertion decoder.nasm. Let me remove all of this stuff in here real quick. And here we go. Now I'm going to paste the modified shellcode with the 0xAA encoded in it. So let me call it, let's say, what do I call this? Encoded shellcode. And then let me paste it. There we go. And now let me go back to writing the decoder. Now, just like what we've done before, I'll get the encoded shellcode address using the jump call pop technique. So we have jump short call shellcode, and here is the call shellcode label. Here is the actual call statement, which is going to call the decoder. Here is the decoder, and of course the only thing I need to quickly do is pop ESI to get the address of encoded shellcode. And here I'm going to type in my decode routine. Now what is it that we want to do? We basically want to take every odd value, which is we want to take this and replace AA with this value. And then we want to take 50 and put it in the location where C0 is. Then we want to take 68 over here and put it in this location AA, right? So of course we would need a counter which slowly increments and allows us to do that. However, we would need two counters. One is to keep track of the next AA and the next value of the real shellcode byte, and the other would be something which incrementally moves along this path to ensure that we actually get back our original shellcode as one packed structure, right? So let me use EDI as the other counter which slowly tracks along the encoded shellcode length. So let me say LEA EDI, and I'm basically going to have ESI plus 1, right? So ESI plus 1 really is tracking the 0xAA at this point, right? Because ESI is pointing to 31 at this point. Now let me quickly initialize a little counter XOR EAX, and I'm going to move the value 1 inside EAX. I'm also going to generate XOR EBX. Right? There we go. Now, what I'm really going to do is the following. Move BL byte ESI plus EAX. Now what does this do? ESI currently is pointing here. EAX has the value 1 inside it. So basically ESI plus EAX is pointing to the very first AA. Now what I really want to do is I need a method by which I can also figure out when I should stop decoding this shellcode. Right? Because we can't just move indefinitely forward, and God forbid there are tons of AAs there just to confuse us in the rest of the program memory. So how do we go ahead and do this? Let me show you how. Now what I'm about to do is basically at the very end of this shellcode in here, I'm going to put in two values, 0xbb, 0xbb, and I'll just explain in a bit what these are going to do. Now, in the next instruction, I'm going to basically do a XOR between BL and 0xAA. Now, please note that till the time we are in the context of the legitimate shellcode, this would end up resulting in a 0, and hence the 0 flag would be set. Now after we end up going beyond the legitimate shellcode, we would end up XORing with BB, and this would end up with a non-zero value. So what this would mean is that we have ended our encoded shellcode, which means we can now comfortably go to executing the decoded shellcode, right, which is exactly beginning from the same location. So I could very easily just do a JNZ short encoded shellcode, right? Now, till the point this does not happen, what that really means is that we are still continuing along the length, and we need to transfer the next value to the location where the next available original shellcode needs to be inserted, right? So how do we do that? Well, very simply, what I'm going to do is move BL, and then I'm going to have byte ESI plus EAX plus 1, right? Now in this context, what I'm really doing is I'm picking the value C0 up and putting it inside BL, and as you probably imagine, the next step would actually be to store it using EDI. So the next step would be move byte EDI, and basically from BL. For a second, let me just tell you what just happened, right? EDI is actually pointing to the next value as pointed to by ESI. ESI points here, which means EDI is pointing here. Now what this instruction has done is it's taken the value C0, put it inside BL, and in the next instruction it is copying C0 to the location pointed by EDI, which is this location. So C0 basically got shifted here, right? So now in memory it's 31 C0, right? Fantastic. Now after this, as you can imagine, we would have to increment EDI so that now EDI points to this location, which is where C0 is currently shown in the figure. So I'm going to do an increment EDI, and of course because the 0xAA is at every even position, we would now need to increment EAX by 2. So I can just do an add AL2, right? And this needs to continue in a loop. So I'm just going to do a jump short decode, right? So this would again go back in here, and this would continue to happen till the time we do not hit an AA at the even location. And when that happens, immediately we know that we have finished our decoding, and transfer goes to here where our shellcode executes, right? Hopefully everything is okay. Let me go ahead and run this. Looks like one small error somewhere, 14. Did not have this. Let's go back in here. Everything assembles fine. Let's use object dump to quickly check we don't have any nulls. Right, we don't have any nulls. Let's cut out the shellcode. Copy this in. Let me open shellcode.c. Compile, and let me now run this. And awesome, if you notice, now we have our bin sh shell just as expected. Let's quickly actually look at GDB and see what was really going on in all of that decoding, right? Okay, here is where we are. And our encoded shell code, if you can quickly recall, starts from basically this location, right? Just below the call, right? So what we really want to do is that we basically want to look at how this is changing over time, right, in each single iteration. So let's go ahead and basically do the following. I'm first going to ensure that we are looking at the shellcode. So let's say x can do a 20xb, add this address. Okay, and now if I were to look at my file, which is shellcat insertion decoder.nasm, you would notice that it's 31 AAC0 blah blah blah, which is exactly what this is, right? So the first thing I'm going to do is also set up a breakpoint in there so that, you know, as soon as the decoding finishes, we know that things are going on fine and we can see the decoded shellcode. And now I can just quickly step through the instruction set to see how the shifting is happening, right? So let me go ahead and do the following. Let me quickly just do a couple of step eyes. Define hook stop, disassemble. Right, so let me kind of go ahead and run this a couple of times. If you notice right now, basically the insertion encoded shellcode is just as is, simply because we haven't entered the loop in there. We hit enter a bunch of times so that we are in there inside the loop. Right, now this is the first place where the move is going to happen, and Right now nothing has happened, but you will notice that just after this instruction, C0 would actually be shifted to this location, overwriting this A. Awesome. Do you notice C0 overwrote it? Now the next time this runs, basically 50 would end up overwriting this location in here. So let's go through this real fast. Right? That is actually a simpler way to do it. I'm just being stupid here. I could basically just do a breakpoint at this location. Right, so I'm going to have a break star. Paste. And let me continue. There you go. And if you look at this, 50 overwrote it. The next time this runs, basically 68 would override this AA. There you go. And now 2F would end up overwriting 50. There you go. And now again another 2F would end up overwriting this AA in here. There you go. Now while this is happening, if I quickly disassemble this location, you would actually notice that your original shell code is kind of slowly starting to come through, right? Let me paste this in here. Do you notice that? We see our little push, our XOR EAX and push EAX and all of that. And if you remember, this is really nothing but execv stack.nasm kind of slowly coming out, right? Here it is. Here is the next value. That's slowly happening, right? Continue. And this would keep on happening, of course, as we keep moving the original shell code back into its logical position. Now, what I'm going to do is basically we could just go ahead and continue and see all of this happen. Right? And I could just quickly kind of see that the whole shell code would be transferred in this way, as you can clearly see. There you go. Now breakpoint 2 was hit, and we basically have our shell in place, and all the disassembly has happened, right? And I just wanted to save for the last one, but fortunately couldn't happen. So let me quickly, rerun this, no problem. I'll just set up everything quickly once again. Set a breakpoint for code, run, disassemble, set up our breakpoint just after the call instruction in here, which is basically this location, so that after the whole decoding can happen, we can see that we have our original shell code back. Continue, disassemble, and here we are, right? If you notice, this is exactly nothing but the execve stack.nasm shellcode, and all of that has now been finally decoded by our insertion decoder, and we continue execution. Awesome. So hopefully this example was crystal clear. In reality, guys, what I'm really trying to tell you is use your creativity and imagination, right? As I said, writing a custom encoder is really you creatively envisioning how you would want to shift things around, or encrypt things or encode things, and it isn't very difficult if really you want to use this for your own personal purposes. Now the difficult part, as I mentioned, would be if you want to make this open for everybody's use, then it's going to be basically a cat and mouse game between you and the AV and IDS manufacturers, right? Okay, awesome. Try this out, try out variations. Think about what would happen if instead of AA we inserted random values. In that case, would you use the length, or could you use something else, some other marker through which you could know when your shellcode ends so that you can move along with the execution. Think about it, write a couple of snippets yourself to gain more confidence. So that's all I have in mind for this video. Thank you. Hello all, welcome to part 11 of the SLAE course module 2, and in this video we will look at how to write a XOR decoder using MMX instructions. Now before moving into it, as you know, there are tons of other instructions apart from those which we've seen, and you also have instruction sets specific to the FPU and extensions such as MMX, SSE and SSE2. Now it's probably impossible for me to cover all of this, but in this video I'd like to illustrate how you can write shellcode using some of these instructions. Now what is the advantage of using these unconventional instructions in your shellcode? Now the most important is existing popular shellcodes hardly use them, and what this would automatically mean is AV and other analysis tools would have lesser detection capabilities for these. Now what you will see in as course of this video is it's very easy to replicate existing functionality by using these extension instructions. So let's go ahead and build our XOR decoder, but this time using MMX instructions. Now MMX instructions are single instruction multiple data instructions. What does that mean? Well, they operate on blocks of data at the same time rather than individual bytes. There are 8 registers from MM0 to MM7 which are part of the MMX family. Now each of these registers are 64 bits wide and can load 8 bytes, which is a Q word at any given time, and this is the chunk of data you want to work with at any given point. Now if you'd like to move data into any MMX register, you use move Q or move Q word, and if you'd like to XOR 2 MMX registers which have 8 bytes each loaded in them, then you do this using the pxor instruction. Now the only thing I'd like to point out that in contrast to our previous XOR decoder, in this case rather than operating on single bytes, we are going to operate on a chunk of 8 bytes at a given time. So let me show you. Now I have my XOR encoder, which is exactly what was there before. Let me go ahead and create some shell code for this. So execve stack. Let's quickly verify this shell code so that we are sure about what we are using. Oops. Compiling. Let's run it. Fantastic, shellcode works, right? Now let me paste this inside our XOR decoder. And create basically the XOR encoded shellcode, right? Copying this out. The length is 25 bytes, something you need to remember. Let me copy template.nasm in here, and we just move template.nasm to mmx XOR decoder.nasm. Let's delete all of this thing here. There you go. And let me first paste in our little shell code. Encoded shell code, define byte. Now to retrieve the address of the encoded shell code, I'm going to use the jump call pop technique. So let me type that out. Jump short call decoder, call decoder, call decoder is in here. And you have pop edi, and this basically gets us the address of encoded shellcode in memory. Now what I'm going to do is we've gone ahead and encoded it with AAs, right? That's the thing we've used for XOR. So I'm actually going to add decoder value define byte 0xAA, XAA, XAA, okay. Just copy this out and just want to make it very apparent that that is the value, so I'm not using any shortcuts. So we have 4 and 4, 8. So pop EDI right now actually gives us the decoder underscore value address, right, which basically means it points us to these 8 A's which you're going to use to decode. So what I'm going to do is I would also like to load the address of our shellcode into ESI. So ESI would basically be EDI plus 8, right, compensating for these 8 bytes which we have defined here. Now I want to run a counter, but remind yourself that right now I'm not going to run a counter for 25 bytes, right, because the MMX instructions operate on blocks of 8, which means we divide by 8, a little bit more than 3. So let me go ahead and move 4 inside the CL register. And now let me write the actual decode loop. This is where the MMX instructions come in, right? So I want to move chunks of 8 byte inside. So I said move Q, and MM0 is one of the registers. Move Q word pointed by EDI. Move Q, MM1, Q word pointed by ESI. Now ESI is actually pointing to the shell code, while EDI, if you remember, is pointing to our 8 bytes of decoders. Now I would like to XOR both MM0 and MM1 and store the result in MM0. So I use pxor MM0 MM1. Now I'd like to go ahead and store the result back by overwriting the encoded shellcode part. So all I'm going to do is again basically a move Q, and this time it's going to be Q word pointed by ESI, so we're going to overwrite the exact same value with what is there in MMX after the XORing. Then we need to move on, so we're going to add basically to ESI the value 8, right, so that we move on and get to the next 8 bytes of the shell code, and I'm basically going to loop back to decode. Once we are out of the loop, which is 4 iterations happen, which is 32 bytes, and you're probably thinking this is more than 25, but we really don't care, right? We would end up overwriting, but because this is an exec shell code, we will never enter that space of other bytes and try to interpret them anyway. Jump short, and then we finally are going to jump to our encoded shellcode. Encoded shellcode. There you go. Right, looks okay to me. 3, 6. Okay. Let's assemble and link this. Just check it one more time for all the values. Call decoder looks okay. Call decoder is up there. Decode. Okay, looks okay to me. Let's observe this with object dump just to ensure that there are no nulls in here. Okay, seems to be null free. Copy this out. Open up shellcode.c. Paste. Compile. And there we go, right? We get our shell. Fantastic. So that's exactly how you build a XOR decoder. And now I just like to leave some exercises for you as well, which you can try on your own. So another way actually to get the address or get program counter is to basically use FPU instructions. And typically the one which is used is the FSTENV, which allows the processor to store the current environment on the stack, or basically memory location which you use along with FSTENV. Now the order is the control status tag word followed by the instruction pointer, data pointer, etc. And really what it does is it points you to the last instruction which was executed in the FPU. So if this is the order FLDS, then this would basically have the address to this instruction stored on the stack. We use C because it's actually the fourth word. So this kind of ensures that by using this, the top of the stack effectively points to the instruction pointer, right? I've also given you a reference where you can read more about it. So this is how you can actually use MMX, or if you research more SSE, SSE2 extensions, or even the FPU for different tasks in shell coding. Now I would highly recommend doing this and try to rewrite much of the existing shell code using these instructions, because the detection rates for these would be very, very, very less compared to those of popular shell codes. So that's all for this video. Thank you. Hello students, welcome back, and in this video we will talk about polymorphism. Now before getting into what polymorphism is, let's try and understand the need for it, right? Now if you've seen, for example, the execv shellcode and you compare it with other execv shellcode examples on sites like Shellstorm, you'll actually see that most of them look pretty alike, right? And hence it's easy for AV and IDS systems to easily go ahead and create a simple pattern matching algorithm to detect that shellcode. Now because detection is simple, if you just use standard shellcode from any of these websites and the victim has any kind of protection, then definitely your attack may fail. Now, of course, you have encoding and encryption as well, which makes things better. But don't forget that the decoder and decryptor stub, however small, also by themselves are still prone to fingerprinting, which basically means we are back to square one. Now, imagine if this were possible. That is, our shellcode would look different every time we create it, even though the functionality would be preserved. What I mean is semantically equivalent instructions. As you can clearly imagine, this would make detection very, very difficult. And this is exactly what polymorphism is. Now, the origins of polymorphism actually started with the virus world, where Dark Avenger was probably the first person who went ahead and talked about polymorphism and created his Dark Angel mutation engine, DAME. And you can read the FRAC article from where I've referenced this. Now, what is the basic principle behind polymorphic shellcode, or behind creating it? You need to replace existing instructions with equivalent ones so that functionality is preserved, right? You can also add other garbage instructions which do not change the functionality in any way, and these are called nope equivalents. Now, nope is an instruction which basically does nothing. And if you're into exploit research, you probably heard things like nope sled and all of that. And you know that nope sled is the easiest way to fingerprint that probably an attack is underway. Now, based on these two principles, let's try and create a polymorphic version of our existing shellcode. So what I've done is I have the execv stack.nasm file, and this is exactly what we have discussed before. Let me copy this out to execv stack from nasm to poly.nasm. Open it up. Rename this. And let me actually just keep the bin sh1 and let me remove everything else. Get rid of all the comments as well. And I could just go ahead and assemble link it and just try out the shellcode in its original form. Just so we know everything's right before we start messing with it. And fantastic, it works. The shellcode length is 25 at this point. Okay, so now let me open up Poly and let's start messing around with the instructions. Now, you're probably thinking the easiest thing to probably fingerprint would be these push instructions, right? Because these show some variation of bin sh with those extra slashes. And if you look at most commercially available shellcode, you will see the exact same push patterns appearing again and again, depending on the specific program you want to execute. The actual hex immediate value may be different. So now let me go ahead and modify this in some intelligent way. So we'd still like to push these values on the stack. Let's see if we can do this in a slightly different way. So what I'm going to do is, let me replace the push with move instructions, right? And what we're going to do is, after the move on the stack, we will set ESP right by ourselves. So let me do this, move tword ESP -4, and let me copy this value in. And similarly, move tword ESP -8. Let's move this value in. There you go. Let me comment these two out. Now I need to adjust the stack pointer. So I could very simply do a subtract instruction. So you have sub ESP8, right? And all this arithmetic is simply because the stack grows from high memory to low memory. Now let's go ahead, assemble and link this. Let's use object jump just to verify that we don't have any nulls in here. Okay, so if you notice, there are no nulls. Now notice something interesting. In this case, the number of opcodes in this line is actually 7, while in our little cut here we only allow up to 6. So this is really an example of how tools can fail if you're not aware of what they're really doing, right? Let's set this to 7 in this case. We'll pick up the shell code, open shellcode.c, and paste it in. Now let's compile it and let's run it. And fantastic, we now have again the bin-sh shellcode where the push instructions have been replaced. Of course, if you notice, basically we've had an increase in shellcode length. It's 34, I think, from 25, 9 bytes increased, which is collateral damage of the polymorphism which we did right now, right? Let me go back in there and see if we can complicate things further. So the second thing I'd probably think is maybe an AV or IDS, apart from the push, it may also fingerprint this exact value, right? Which we still seem to be using in both of these instructions. So let me try and change just the first one into equivalent instructions so that we can replace the whole 68, 73, 2f, etc. And to be honest, guys, what I'm really trying to tell you is there are probably a zillion ways to do this, right? There's no right or wrong way. Depending on how much space you have to accommodate your shell code, you'll just have to be watchful about the size of the code you create when you apply all of these other polymorphic techniques to it, right? So let me try and make a change. Let's use the ESI register, right? Move. What we can do is ESI. Let me put in a value. And what I'll do is, just as an example, I'll decrease each of these by 1, right? So this becomes 5, 7, 6, 2, 1, E, 1E, right? And then I can just do an add ESI 0x1, right? And then I now go ahead and do a move instruction in this case, and this move instruction would be to move the D word, again the same as the one on top, ESP -4, but in this case we pick up the value inside ESI, right? So this one instruction has now been expanded into these 3. Let me just quickly do a check. This is basically 6873, 6873, looks okay. 2F, 2F, okay, looks fine to me. And let me go back in here, follow the exact same process. There you go, right? the shellcode length is now increased to 41, right, from 25. Note that. So, depending on how you write your polymorphic code, the size can increase or decrease. Typically, it's a good idea to kind of scout around and look at instructions which would end up decreasing the size. Now, you could, as an example, change this as well. These two instructions in here. So let me change the XOR so that we use EBX as well. So I can do a move EBX, EAX, and then I can do a XOR EAX, EBX, right? This is equivalent. Then I could change again the push EAX if we really wanted to a move dword ESP -4 EAX and then subtract ESP4. Right, I can also add instructions, as I said. Now, all of what we've looked at currently changes just the instructions we are using while preserving functionality, right? You could also add instructions which make no sense. So as an example, I could clear the direction flag here, CLD. I could set the direction flag in here. Again, you're not using it, but this just adds to the fact that our output code would now look very, very different. Let me just quickly look at it with object dump just to ensure we don't have any nulls. There we go. So quick screening here shows that the nulls aren't there. Now I can basically rip this using object dump. Copy this back in here. And there you go, it works, right? So we've added a ton of changes. The casualty, of course, was the shellcode size increased, which means now we can again start working on those instructions to see how we can reduce the size of the shellcode, right? And as I said, the size of the shellcode pretty much depends on the specific circumstance in which you're using it. Personally, I think 51 is not bad, but you could reduce it further. Now, this is exactly what I did right now in a very manual way, is something a polymorphic engine would actually do in an automated way. Now, there are polymorphic engines available. Some of them are outdated. Some of them would need a little bit of more work and rewriting. Here are a couple of them. You have AD Mutate. I've also given you a YouTube video where there's a DEF CON talk on using AD Mutate. Then you have CLET, which was published in the FRAC magazine. And as I said, simply because polymorphic code originated in viruses, I've also given a mirror link to VX Heavens where you may be able to find examples of other such engines. Now, writing your own polymorphic engine is more of a development exercise and is beyond the scope of this tutorial or this course for that matter. And I would really say in most cases you could just handcraft your own polymorphic engine, unless it's like you want to produce shell code, in a mass way with a specific polymorphic engine which you've written, right? But if you need examples, I think AD Mutate has a good amount of code in there which you can have a look at. So that's all for this video. Thank you. Hello students. In this video, we will look at analyzing third-party shellcode. Now, why is this important? I'm sure all of you have encountered strange-looking shellcode in exploits in different forums, or even on sites like shellstorm.org or exploitdb. And to be frank, would you really want to run something which you don't understand? For all you know, it could be an rm-rf star which could delete everything on your computer, or for all you know, it could be a download and execute shellcode which executes some sort of a backdoor. So it is very, very important that you understand what a piece of shellcode does regardless of its source. This is where analyzing shellcode comes in. Two primary reasons. The first is you should definitely know each and every bit of what is running on your computer, especially shellcode. And the second is you can learn a lot by understanding and looking at other people's shellcode, especially from the experts who've been doing this for quite some time. Now, the reason is there are a lot of small tricks here and there. There are instructions which can compress your code to a pretty great extent, but unfortunately, all of these little tips and tricks are hidden in the shell code and are not properly documented in blogs or books. So that is another big reason, and this is true for any development based activity, is you can learn a lot by looking at other people's code. Now, to analyze shellcode, we can use GDB, ndisasm, or run shellcode inside an emulator such as libemo. I leave the installation of libemo and ndisasm to you. It's pretty straightforward. You can install it on your Ubuntu machine. Now, the exercise I want to do is take a piece of staged shellcode and understand what is happening. Now, a staged shellcode is a very interesting creature. It is divided into two stages. The first is a very small stage, and all it does is it loads the second stage. Now, the second stage can be available via input or over a file, or in a file, or over a network, right? After the first stage loads the second stage up, it passes control to the second stage, which then executes. Now, you're probably asking yourself, why do we need all of this? The reason is, many a times in exploits, the amount of space available to run your shellcode is very, very small and limited. So small sometimes that it is not possible to do any meaningful task within that space. In such a case, it would be better to first run a very small stub, which in turn would import a much larger payload to do a greater job. And this is exactly why staged shellcodes or payloads are used. So let's analyze an existing staged shellcode. I've taken a simple example, and this staged shellcode requires the second stage to be given to it via stdin. It's written by under fkz, and it's available on shellstorm.org from where I've picked it up. There's the URL. So let's go in here. Inside the analysis folder, and I have my execve.nasm, and I think right now the bin ls is enabled. So let me just verify this. Do a quick cut, pick this up, paste it in, run it, and it should do an ls in the current directory as expected. Now I'm going to pick up the staged shellcode from shellstorm, copy it inside shellcode.c, now I need to feed in the second stage, which was basically execve bin ls, to the first stage, which I can do using the echo command. There you go. And if you notice, the first stage is executing the second stage, which is now basically printing ls on the screen. Fantastic, right? So this is how a much smaller stage of 14 bytes was able to execute a much larger payload of size 25 bytes. Right? So imagine if the amount of space was only 15, then you would not be able to fit the 25 bytes inside this. So you would use stagers in which the first 14 bytes would load the next 25 bytes and then execute it. Now, let's go ahead and understand the shellcode better. And one of the ways is to use NDISASM. Please note the last dash in there. And this gives us an immediate disassembly of what's in there. This is the offset from the start, the leftmost column. The middle column is basically all the opcodes, and the right hand side is the disassembly. And you can clearly see that this is ending up calling execve, and here is our little push, right? Now we could go ahead and do the same for our first stage as well. So we could just copy it from here. Could run a new one, echo. Now this gives us a disassembly, and looks like we do a bunch of push and pops and finally call int x80, which is basically we are calling a syscall. Now this seems a bit confusing, so let's use something slightly more powerful, which is GDB. So currently /shellcode, if you remember, contains the first stage. So let's go ahead, open it up, and break, as you already know, is going to be here. Set disassembly flavor to Intel, then run. Okay, so this is the same piece of shellcode, which is the first stage in here, and we have the pushes and the pops, etc. happening, right? What really catches my eye is the syscall, and I'd like to understand exactly what parameters are being passed to the syscall to figure out which syscall is happening. Now, one way is to actually traverse through this whole set of instructions and figure out what is inside EAX, EBX, etc. The other way is just before the syscall happens, let's set a breakpoint. And when we hit that breakpoint, let's analyze the value of the CPU registers to figure out which syscall is happening and what are the values being passed to it. Continue, we've hit it. Assemble, here we are. Let me print $EAX to figure out the syscall number. Syscall number is 3. So let's figure out what is syscall number 3. So syscall number 3 is read, which is we are reading data as expected. The first stage has to read the second stage. Let's look at the man page. Read takes in 3 arguments, which need to be in EBX, ECX, and EDX. The first one seems to be a file descriptor, right? Let's look at what was given inside EBX. Interesting, it's the value 0, which stands for std in, right? Std in is 0, std out is 1, std error is 2, and after that all the other numbers are then allocated to any additional files which may be opened. So which means we are reading from std in. Great. The second argument, buff, is basically attempts to read up to count bytes from file descriptor into buff. So buff is where the input which is fed from std in is stored, and read is going to read count number of bytes from input, right? Which means ECX would point to the buffer, and EDX would point to the number of bytes, which is 7F. And if you print that in decimal, it's 127, which if you kind of go back in here, the code reminds you that 127 bytes is the maximum which can be read, right? Now it's slowly starting to make sense. Right, fantastic. Now, if you also parallelly look at the code, you would notice that we've used ESP somewhere. So if we try and print ESP, looks like ECX is basically nothing but containing the address to the top of the stack, right? Which is okay. We basically want the input to be read on the stack. Fantastic. So what we need to do now is just verify. After this, if you notice, the interrupt returns, and let's see what happens. So let me go ahead and do a quick step I. So this is waiting for input. Let me put in A, B, C, D, E, F, G, H, I, J, K, L. This would have been your shell code, by the way, which you fed in from stdin. Returns, disassemble. Now this says push ECX. Now before that, let me look at the contents of ECX, right? This contains the address. Let's examine this address. 10. Aha. If you notice, this is nothing but the input which you just put in, right? A, B, C, D, E, F, G, H. Fantastic. Now the next two steps are interesting. We push ECX on the stack. So if I look at, oops, right? So this is currently what the top of the stack contains, and after that we have ret. If you remind yourself, ret is going to pop the top 4 bytes of the stack and put it inside EIP and begin execution there, which means this is what is now going to be what EIP would point to. And what is this really? As we've seen, this is what is pointing to the shell code which we entered as input. Here, it's the same address, right? If I continue, of course, the program would crash because this isn't any shell code. But as you clearly understood how the staged shellcode works. So this is the very first stage, and all it does is it takes that input from stdin, stores it on the stack, pushes the address of the top of the stack in the stack, and then with ret makes that the next instruction to execute, which means EIP now points to our shellcode which we sent in as stage 2 from input, and our shellcode executes, right? Fantastic. Now this is really how I would want you to analyze shellcode, and we'll take up a couple of new examples. To be honest guys, if you really went through these 60-70 odd shellcode demos in here for Linux x86, I really think you'd practically be able to create any shellcode which you like, simply because the examples are so varied and so exhaustive. So I'd highly recommend that if you have the time, go through each and every shellcode in here for Linux x86. Anyway, there are also network-based stage loading. For example, you could have a bind TCP which binds a shell to a TCP port which could be staged. Similarly, reverse TCP shell. And of course, if you've ever used Metasploit, the Meterpreter itself is a staged payload where you have a small stub which finally loads the Meterpreter DLL and executes it. So that's all for this video. Thank you.